This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Got Chuck Nice with me. Chuck?
Yes, sir. What's up, Neil?
All right, we're doing cosmic queries today.
Yes, it is.
But beyond category.
Cosmic grab bag.
Grab bag?
Yeah. All right, this is Jiraj Belangi. And Jiraj says, is it theoretically possible to develop a space drive that would have constant acceleration, hence creating constant artificial gravity?
That's what rockets do.
Okay.
Okay.
But he means continuous, like we're going to Mars.
Yes.
And so you're burning the entire time that you're going.
If you do that, you'll get there very fast. Like, so this 9-month journey that we talk about going to Mars, 3 days to the moon, 9 months to Mars, you know what that is? Mm-hmm. That is aiming for where the object will be when you arrive.
Gotcha.
Fire your engines enough so you don't fall back to Earth.
Right.
Okay. And you need enough energy to cross over to where your destination's gravity exceeds the gravity of Earth.
Right. So it's basically like that planet, when it gets to that, it lassos you and then starts pulling you towards the planet.
It's like climbing to the top of a hill and then you can just roll down,
the hill.
Okay.
Right.
So you're climbing out of the gravitational well of the Earth, and it's getting weaker and weaker and weaker. But as you're getting towards the other object, it's getting stronger and stronger and stronger.
Right.
There's a point where they balance. And if you cross over that point, you just fall towards your destination. Correct. Once you launched yourself with enough speed to get there, there's no engines firing.
Right.
And once you cross over, no engines firing, you just fall in.
Right.
You need your engines again to not crash. Okay.
Right.
Because you're accelerating all the way there by the action of the planet.
Right.
All right. To Mars, that's a minimum of 9 months. If instead you accelerated the whole time, then you still want to slow down. So you'll accelerate till you're like halfway there, then turn around and then decelerate the rest of the time.
Captain, we're approaching the planet. We got to fire the retro rockets.
Yes, except this would be a sustained thing. And that way you would maintain a certain artificial gravity, because an acceleration of a rocket is an exact mimic of being on a gravitational surface.
So the only sci-fi show I've ever seen that does, and I recognized it from you telling me exactly what you just said years ago, it's called The Expanse. And I had so much respect for them because they show a ship headed towards a planet, and the engines you see first firing as it's moving towards the planet. So it's like the entire time that they're showing you, like, oh, they're headed to whatever planet. And then they show you, and it looks like the ship is going in reverse.
Oh, interesting.
Yeah, but exactly why you said, because they're firing the rockets to slow down. To approach the planet.
Correct.
So cool.
But there's another interesting fact here. While you are firing rockets, there is a force operating on you that you will not be able to distinguish from an ordinary gravitational force. This was deduced by Albert Einstein in what's called the equivalence principle. An accelerating rocket is indistinguishable from you sitting on Earth with Earth's acceleration of gravity, if the two accelerations are equal.
Right.
There's no experiment you can perform other than looking out the window to know if you're in a rocket or sitting here on Earth in a box.
Right.
Okay. So now, what's that movie that had moon pirates?
Oh, that was called Ad Astra.
Correct.
That's right.
Okay, Ad Astra means to the stars in Latin.
Right.
This is a deep phrase that we've been using in the space community forever.
Right.
And interestingly, it's on the state flag of Kansas. So they would show these rockets firing, and you go inside the ship, and they were all weightless. No.
That wouldn't work.
There's this misconception that being in space
makes you weightless.
No.
Right.
No. If you are drifting in space, as our space missions do, they're sent in motion and you're drifting towards the crossover point, and then you fall in. Oh, there you go. You're weightless that entire time. But as long as you have on rockets, you are not weightless at all.
Look at that.
Yeah.
Super cool, man.
Yeah. So, so you could do it, but, sorry, getting back to the question.
Right.
You need fill-in stations along the way.
What?
If you're going to drive straight from New York to LA,
that's right.
How big must your gas tank be?
Well, that's yes.
Okay, so we have gas stations along the way. So if you really want to accelerate to your destination through space, you need filling stations parked throughout the solar system.
Right.
And you reload and keep going.
Right.
But we're not there yet.
Or like in Star Wars where they have the ship that is part of another ship. So there's one ship that gets you to hyperspace, but then when you come out of hyperspace, your ship leaves that ship, and then you can just ride normal.
Okay, so something else did all the heavy lifting. Yeah. Okay,
Cool,
all right.
man. Very, very cool, Jiraj. Thanks for the question. Here's Ryan.
Oh, and just while I'm there,
Go ahead.
when you're in orbit,
Right.
you're freely falling towards Earth. There are no rockets keeping you in orbit.
Yeah, you're just falling around the Earth.
Around the Earth, and so you're weightless there. It's not because there's no gravity in space.
Right.
All right, we have it's a delusion, not a delusion. We've been misled to think that the act of being in space is synonymous with being weightless.
No,
that
it's the
is not
same as when
case.
you're on that, what's it called? The Vomit Comet? What's that thing
Vomit
called?
Comet, yeah. The airplane.
The airplane.
Yeah, it goes into a controlled, into a parabolic dive
Right.
where you're falling towards Earth.
Exactly.
It's basically, for that short period of, for that short bit, it's sort of orbiting Earth.
Right.
Did you have physics in high school?
They taught it in my school.
One of the things you learn is that a projectile has a parabolic arc.
Right.
Okay? And there's a formula for parabola, and you can solve how far, neglecting air resistance, you can know how far a projectile will go.
First use of computers.
Yes, in fact, it was. Well, for the military.
For the military.
They want to know where the bomb's going to fall.
Where the bomb's going to fall.
Okay.
You got to be able to figure out the trajectory of mortar shells.
Turns out, it's not actually a parabola.
Oh, okay.
It's very close.
Right.
But it's not a parabola. It is the segment of an orbit, an elliptical orbit.
Gotcha.
If the entire mass of the Earth were at its center.
That makes sense.
Okay?
That is so cool.
Yes, it's completely cool.
That is so
you take
cool.
all the mass of the Earth, collapse it to a point in the center, and watch this go in orbit around
that point.
Around that point.
That's right.
So, but it doesn't succeed because Earth gets in the way.
Exactly.
But the forces controlling it is what's the mass of the Earth and what's its distance from the center of the Earth.
Right.
That's all that matters.
That's so
you
cool.
collapse all the mass there, and then you have it.
Fantastic.
Yeah. So even when you're
in like the space station,
the
you're
space
just
station,
falling
you're
around
the Earth.
Very, very
Correct.
cool.
Mm-hmm.
Very cool, man.
All right.
All right, here's
Next.
Ryan A. He says, hey, Neil, maybe Chuck, Ryan from Toronto here. My question might be obvious, but time dilation has been messing with my mind.
As it should. But
Exactly.
no one should be comfortable with time dilation. Okay?
Right?
Mm-hmm.
Yeah. Once, you said that a photon doesn't experience time. It's born and immediately is destroyed. If a photon from somewhere in the galaxy is born, and over time, it redshifts as we know photons do. How can it both experience a redshift, but also be destroyed immediately after creation? Thanks. Love the show.
That's a great question.
It really is.
I don't know that I have a good answer for that.
I do.
So what he's saying is, if the photon that's emitted is different from the photon that you detected or destroyed at the end of its path, then something happened to the photon. So if something happened to the photon has to be temporarily aware of that in some way.
Right.
I'm thinking that's what he means. I'm pretty
makes
sure.
sense.
Pretty sure.
Yeah.
So we see this. The question is, what does the photon think happened?
Right.
Now, since it's emitted at one wavelength and detected at another, I got to think about that.
That's something, huh?
Because the photon would have to say, I'm redshifting. But to even be able to say that, time elapsed for you.
It's exactly.
Because you was something yesterday and something different tomorrow.
Right.
Yep.
That's pretty wild.
No, I don't have a good answer. You know who might have an answer is Jana. Jana, friend of the show.
Yeah, exactly.
She's a cosmologist.
Somebody call Jana. All right, well, listen, that's a very good question, Ryan A. And,
yeah, sorry, I'm sorry.
And who knows? Who knows what the answer is?
I have to ask the photon. I'll get back to him.
All right, this is Amar Shah. And Amar Shah says, greetings, Dr. Tyson, Lord Nice. This is Amar from Sydney, Australia. is it possible mathematically that our universe is on the other side of a black hole? And could there be more universes on the other sides of black holes? I think, does he mean our galaxy? Because
I have a book on the shelf that goes through the mathematics of what's on the other side of a black hole.
Of a black hole.
Right.
Right.
And if you fall in, your time slows down relative to what you just came from.
Right.
And you'll see the entire future history of the universe unfold.
Right.
As you go down and emerge, a whole other space-time opens up in front of you.
I gotcha.
The mathematics of general relativity gives you that.
Right.
No one has tested this, but general relativity works in all these other ways. And this is a prediction of something that has worked so well.
Mm-hmm.
It's intriguing. Certainly worthy of at least sci-fi treatment before we get actual data. So the universe that has the most universes is the universe that has the most black holes.
Right. Now, is it a different universe or is it a residual universe?
Call it what you will, but there's you can't go back and forth.
Of course you can't.
So by our operational definition of universe, you're in another universe.
You're in another universe.
And don't denigrate it by calling it residual or universe light or dwarf universe.
Okay, I got you. Well, that's very cool. So mathematically, it does work out.
Yes,
that's how
it does.
works.
Mathematically.
All right, cool. This is Eduardo.
Oh, by the way,
yeah,
the horizon of the universe, has this is beyond which you cannot see.
Okay,
has all the same properties as the event horizon of a black hole.
Oh, so cool. So what we see is the edge of our universe that we can observe as all the same properties as the
same mathematical properties as the event horizon of a black hole.
Wow, I didn't know
so
that.
We would be living evidence of a universe inside a black hole.
Would be. That's crazy.
It's freaky.
Yo, that is, damn.
That's good.
Somebody get me an edible. All right, this is Eduardo Mancilla. Hello, this is Eduardo writing from Mexico. All right, so Eduardo says, I saw a video on strange matter, but I didn't quite understand what exactly that is. Could you maybe talk a little bit about what it is and how it forms? Strange matter. Yeah,
I'm not up on the very latest there, but there's actually good precedent for having this mysterious thing happen in our particle accelerators. And we say, we can't explain this. There must be some particle we haven't discovered yet accounting for this inexplainable stuff.
Ooh.
For this behavior of the other particles, they're responding to something that we can't see and don't know how to figure out how to detect it yet.
Right.
So let's invent the idea of this particle. Doing that has enabled the discovery of multiple particles. Assume something's there.
Right.
What would its properties be to cause all the confusion that it does?
Right.
Let's look for it.
And then look for it.
And we found it.
Look at that.
The neutrino was one such particle.
Look at that.
All right. There was a reaction of particles, and at the end, the charge all worked out, but the momentum didn't add up. So we have a law of conservation of momentum. It's never been violated.
Right.
All right. It was missing some momentum. Way to go. All the same, we took account of all the particles.
Right.
And somebody said, a particle must have taken away the momentum. I don't know where. Go look for it. And we knew it didn't have a charge, so it was called little neutral one.
Little neutral one.
Neutrino.
Oh, cool.
Yeah. So there are things we cannot explain. Dark matter, dark energy. There are these phenomena in the universe where we are kind of, I don't know, I want to say we're giving up, but we'll say, we don't know what it is, okay? Just call it anything, okay? Is it some new kind of matter? Is it strange matter? Is it, and there's a whole catalog of names for these particles that are not yet discovered. And many of them are fanciful.
Wow.
So it's like a zoo.
So is that like missing spaces in the periodical chart?
Oh, very nice.
Yeah.
Chuck.
Okay, cool.
Very nice analog there.
All right.
Because that's complete now.
Right.
You know, on many things you can say, we got this.
We got it.
Move on to the next problem.
Right.
But we got this.
Right. But there was a time when they had to leave a space.
They left the space.
Hey, we know something's going to go there.
Right. And, you know, one of them was discovered, I forgot exactly when, but it was not discovered in nature. We had to make it.
Oh, right on.
Okay. Do you know the word for when you make something?
Manufacturer.
Yeah. Tech.
Tech. Oh.
Technology is you made it.
Right.
You didn't get it from nature.
Right.
Okay? We forgot that because it applies to everything today. Tech, okay, so it's called technetium.
Technetium.
Yep. We made that made that element.
That's pretty cool.
So of all these hypothetical forms of matter,
Right.
all right, one of them has been named for a variety of quark
Okay.
that we know. Quarks have fanciful names,
Yeah.
okay? There's an up quark,
Right.
a down quark,
Right.
a strange quark, a charmed quark, okay?
Well, a wine cork.
Quark. So, and the quarks make up our nuclear particles,
Right.
okay? So there's an up, down, top, bottom, strange, charmed, okay?
Okay.
So the up, down are the quarks that make up protons and neutrons.
Okay.
They have heavier components in the universe that we find in accelerators, but we don't encounter them every day. So all the particles that we know and love have versions that exist at a higher energy level.
Gotcha.
So our quarks are up and down. The next level quarks are top and bottom because they're pairs. And the next level quarks are strange and charmed.
Gotcha.
There's 3 levels of electrons as well,
Okay.
3 different kinds of force carriers. So this is what we call the standard model. Yeah, we chatted about that with
Brian Greene.
Right?
Yeah.
It's been hypothesized that the strange quark, under certain conditions of pressure, temperature, would manifest and be the predominant particle in the object.
Okay.
So it'd be strange matter possibly making a strange star.
Gotcha.
Yeah, but don't overinterpret the word strange. It's just a word to describe a variety of quark. And you know where the word came from? The word quark comes from James Joyce's Finnegan's Wake.
Really?
Yes.
Oh, okay. How so?
Because we found that there were 3 quarks in the middle of the proton and neutron.
Right.
Okay, 3. And there's some rhyme in Finnegan's Wake that says 3 quarks for muster mark. And so Murray Gell-Mann, who's one of the original physicists to think about what the particles are in the
tiny
in
stuff.
the tiny particles, he had that phrase in his head. And then he says 3 quarks for muster mark. And so it was 3 because the number 3 matched.
Is a
Okay,
match.
except there's more than 3. There's like, you know,
Yeah.
with the 2 varieties times 3, there's 6 kinds of quark. So the numbers in the end don't match up.
Well,
But
he didn't know.
he didn't know. He just started.
He just-
right?
yeah.
He just
He was
began
just-
the investigation.
Oh,
but the word quark stayed.
Okay.
Mhm.
Yeah. It's a dumb name.
Well, you can't say, what does it look like, right?
That's true.
I mean, in my field, we see a nebula that looks like a tarantula. We call it the Tarantula Nebula.
Right.
We see another nebula that looks like North America. It's called the North American Nebula.
That's so crazy.
If you see a quark, what are you going to say it looks like?
Well, there is nothing that
That's what I'm saying. These
There's
are
nothing to
particles.
say. It's
There's nothing.
you can't.
Right.
Right. Oh, that's cool. All
Okay.
right. I take it back.
We do have that problem.
Muster mark.
If you ask me, how big is the universe?
Well, how big is the universe?
It's as big as, end of sentence.
It is the biggest.
You can't
Right.
compare it.
Yeah. There's nothing to compare.
I can tell you how many feet will go across it, but that's
Still doesn't make it.
there's no reference
There's
frame
no
for
reference.
it.
Right.
Mhm.
Okay.
Good.
Let's move on to Maurice van der Linden. He says, "Dear
He's from the Netherlands or something?
yeah. Anyway, he says, "Dear Cosmos connoisseurs, Maurice from the Netherlands here."
No, from the Netherlands.
And he was from the Netherlands. Wanting to know more about gas giants.
Mhm.
Why are they named that way?
Keep reading.
All right, I'm going to keep reading. All right. Don't they okay, you look at you, keep reading. Don't they have a solid core and gaseous atmosphere, the same as terrestrial planets? Love the show, keep it up. So in other words, why can't we just call them, bigger atmosphere planets?
Okay, because the difference is on Earth, Earth's atmosphere is to the solid planet what the skin of an apple is to an apple.
Gotcha.
Whereas on the gas giants, their atmosphere is to their solid core what a peach is to its pit.
Okay. That makes sense.
Okay.
I got what you're saying. Because, I mean, we have...
Or
our
small, or
our
smaller.
atmosphere is gas. So
It is gas.
It is still gas. But
It ain't much of it.
But it has nothing to really do with what we are if you were to really look at it.
Well, structurally, I mean, it matters for our life and our ecosphere and everything.
No, I'm saying if you were to take it away, we would still be a giant rock floating in space.
Correct.
There you go.
Correct. You take away the atmosphere of the gas giants,
right?
They'd be unrecognizable.
You got nothing. Right.
Correct.
Right.
Correct. So a peach to its pit or smaller than a pit.
Right.
I'm trying to think of what's a good analog there.
Like an apple to a seed.
Yeah, but that's more seeds, and
yeah,
I have to
more
then
seeds. I know what you're saying.
Right.
You got 6 seeds in there, so we got to have 1 seed.
I'm educator man.
Okay.
And I've had some avocados lately.
All right.
They had really small pits. So somebody's breeding them things to be little.
Yeah.
Like when we grew up.
No, they were giant.
Giant.
Yeah.
So maybe avocado one day would just have a tiny little pit and it'll all be flesh on the outside. That'd be like the gas giants.
Right.
Yeah. So he's right to think, yes, they have a solid core.
Right.
But it's a tiny thing way down inside.
Right.
Mm-hmm.
And let me ask this on
for all of them.
Follow up from Maurice. No, though. Is that tiny core solid because of all the pressure that the gas makes?
They are made out of the same ingredients as we are.
Oh.
Let me be precise.
Okay.
Okay?
All right.
The original nebula that formed the sun and the planets.
Okay.
It's gas.
Right.
Mixed with heavy elements.
Right.
But they're just gaseous heavy elements.
Okay.
The gas giants, when they form, where do the heavy elements go?
To the center.
Thank you. And they make a solid mass there.
Uh-huh.
The lighter elements go up to the top, especially the hydrogen and the helium, and it has enough gravity to hold on to them. They're moving fast, but they're not going to escape because the gravity is strong.
Gotcha.
For our Earth, where do the heavy elements go?
To the center.
How about the gas? The lighter gases, the 2 lightest gases are hydrogen and helium. They're moving the fastest at any given temperature. Right. It's a fascinating law, first discovered by James Clerk Maxwell.
Okay.
We should talk about that.
Oh, James Clerk Maxwell?
No, his Maxwellian distribution of velocities.
Ooh.
Let's do an explainer on that.
We will.
No, it's very cool.
All right.
Really cool.
I'm about it.
Okay, you got it?
Cool.
Okay, put a pin in that.
Okay.
All right, good. So we're trying to hold on to the hydrogen and helium the way Jupiter, Saturn, Uranus, and Neptune did, but we can't because our gravity
we don't
is
have enough
strong
gravity.
and it all just escapes back up.
Goes out.
Okay?
That's really cool.
So we're stuck with the heavy gases, oxygen, nitrogen.
Right.
And carbon dioxide.
Okay,
right.
so that's how that works.
That's how that works.
Excellent.
Yeah.
Oh, man, that was great. Okay, cool. I like when those simple stuff.
And of course, within the solid core, the heavier stuff is in the center of the solid core.
Right.
Right? And what's in our solid core? We got iron. There. And iron is heavier than
everything.
It's heavier than the rocks.
Right.
Rocks float.
Compared to iron.
Compared to iron. Yeah. All right.
Super cool, man. This is Vasco Vukov. And Vasco Vukov says, hello, Dr. Tyson, Mr. Nice. This is Vasil Vukov from Sofia, Bulgaria.
Nice.
We're trying to find aliens, but if we want to hide from them, what should we and could we do even if they point their sensors straight towards us? How stealth could the Earth possibly be?
I love that. Okay, so now watch. Okay.
All right.
You ready?
Go ahead.
Okay. Let's go back in time. TV signals.
Right.
The reason why the old timers, everyone else just won't care what I'm about to say. In the day, you could get radio stations from cities that were far away, but you wouldn't get TV stations. TV waves, you have to be in a direct sight line to the television transmitter.
Okay.
So you have to have a transmitter everywhere for TV. So TV was very local in the day. Radio waves, okay, especially shortwave, but also AM radio, its waves had the right frequency to reflect off the ionosphere of the Earth.
Ooh.
And it could send a signal beyond Earth's horizon.
That's crazy.
Some would leak, but others would bounce back.
Right.
Point is, these modes of communication had leakage, especially television waves. So someone eavesdropping on Earth, and they're, let's say, 80 light years away, they're getting the earliest radio signals that have been emanating from Earth at the speed of light. There's howdy doody.
Right.
There was, and then the TV signals would start coming in. Early TV, the honeymooners. And if they want to decode our civilization.
Right. They think that we're all abusive who like to threaten our wives with violence.
With violence by
Nah.
to the moon.
To the moon.
And that's when people laughed at that.
Right, exactly.
Right. I think they left because she was defiant, even in the face of
Right,
that
exactly.
threat of violence.
Oh my God, you are so funny. You're gonna beat your wife, huh?
Right.
Yeah,
It's
exactly.
crazy. It's crazy times.
It's been crazy.
Crazy times. So that's how they'll learn how men and women interact. That's their benchmark. So this continues throughout all the sitcoms and all the TV. And they'll see the war broadcasts and everything. They get to the 1980s and signals start disappearing.
Uh-oh. What the heck is happening?
People are using cable.
That's right.
Okay. So one of the earliest shows, which I feared would be first seen by aliens, but I think we're protected, is Beavis and Butthead.
Right.
That was MTV, and you got that via cable.
Right.
Okay. That was not transmitted into space. So a lot of what's happening today is protected from leakage for that reason.
Right.
Because it's
a closed system.
It's a closed system. It's cable.
Right.
Okay.
Gotcha.
So that's my first point. Second point, here's just an interesting fact. If you're communicating through space and you have a signal, you don't want anyone to intercept it.
Okay.
You want to encrypt it.
Right.
Okay.
Yeah, well.
The perfect encryption is so well encrypted that it is indistinguishable from the din of radio noise in the universe.
Oh, that is.
Think about it. Okay. If there was something about your signal that was different, then I would know somebody created it.
Exactly.
Okay? So you need something to encrypt it so that it looks like noise, and you have the noise decoder on the other side.
Look at that.
Okay?
And when you say noise, you're talking about the cosmic microwave background.
I need all of the radio noise in the universe.
In the universe.
Okay? If you take a radio antenna pointed anywhere, there's like noise.
Right. Of course, yeah.
Okay?
That's the
static. It's the static.
Yeah.
Okay? So if I see something that doesn't look like the static, there's a signal there. Even if it is encoded, I know there's a signal there.
Yeah, because it's different.
It's different from the static.
Right.
So the perfect encodings would be indistinguishable from static. So if a planet wanted to hide from alien eavesdropping, they would make sure that all signal transmission was so thoroughly encoded that it was indistinguishable from static.
That it looked like the noise of the universe.
Correct.
That's great.
Yes.
That is really great.
Yeah.
I love it.
Yeah. And now it's a little tough because you might have more noise here than somewhere else. Right. That could give you away.
Right.
Exactly. There's the background in, and then there's a bright noise spot here.
So there's an anomaly of
noise. Of noise. Yeah.
Right.
So you have to figure that one out too.
Yeah.
But
that's cool though.
Yeah, it's very cool. Another way to hide from aliens?
Yeah.
You get one generation of astronomers to send a plaque out into space.
Right.
Intended to be read by aliens. This is a plaque from Pioneer 10 and 11.
Right.
Which was launched in the 1970s. And some of this iconography was also used for the Voyager missions.
Right.
But notice at the bottom, there's the solar system.
There's the solar system. There's the sun.
The sun and Mercury, Venus, Earth. And Earth, there's a line coming from Earth that shows where this spacecraft came from. Because this is a life size of the spaceship relative to the two human figures. Yeah, exactly. Okay. So you get one generation to try to talk to aliens innocently, not knowing the aliens are evil, that they're going to come and suck our brains out.
Right.
But let them show a 9-planet solar system.
Right. Yeah.
This one has Pluto.
Right.
They're going to come looking for us because this is our return address, by the way.
Right.
The spider diagram, that's our distance to pulsars in the galaxy. And you can triangulate on that and come right back to our vicinity.
Why would we do that? Why would we ever do that? That is so.
It seemed like a good idea at the time.
That's insane.
I know you wouldn't give your email to another human stranger in the street. So now they come back looking for a 9-planet solar system, and ours is not that.
Okay.
And the reason why would they not think it? Because Pluto is represented in this
as a
planet, as the same size as like Mercury and other objects here, and it's just not.
Guys, we only see 8 planets here. We got the wrong one.
There you go.
Got the wrong solar
keep moving.
system.
Nothing to see here.
Nothing going.
Keep going.
All right. All right, this is Letitia Davis. She says, hey, this is Letitia Davis from Conway, Arkansas. So
nice.
How many early cosmic discoveries were made by curious observers with no formal training? Is the frontier still within the reach of amateurs, or has science advanced too far for a layperson to contribute to the cosmic perspective?
Love that.
Wow, look at that.
Very good. Very good.
All right, Letitia.
So let me give something that's not an answer to that just yet, because I just want to put it out there. I wrote an essay many moons ago called Stick in the Mud Astronomy. I think it's online. Stick in the Mud Astronomy.
Okay.
If you have a stick and you put it in the ground,
Right.
what can you deduce about the operations of the universe from just a stick in the ground? Okay, you can invent a sundial. You can track rising and setting points of the sun on the horizon and the moon and all of this. Okay, so you can do quite a bit. It was an homage to ancient peoples who didn't have telescopes.
Right.
There's a whole essay on that called "Stick in the Mud Astronomy." All right, without access to frontier telescopes, you're not going to discover dim things.
Right.
Because you're just not going to ever see
them.
Can't see them. However, there are more amateur astronomers in the world than there are professional astronomers. Okay?
Right. Yeah.
And they all have like backyard telescopes. That's fine. Very accessible. They're looking up all the time. Amateur astronomers have famously and historically discovered comets.
Right.
Discovered supernova, although we have supernova surveys now that are very efficient. You might not be in line for that. But if you see something, say something. Okay? We have a clearinghouse because phenomena that comes and goes, we don't know about.
Right. Right.
We can't, I have a telescope for one night and I'm looking and I go home. That's why we have the Vera Rubin telescope, which is basically going to be taking video of the universe, of the whole sky. So you can watch in case something shows up and goes away or disappears. You know what else we'll discover? Every one of Elon Musk's satellites coming across. That'll contaminate the data where we're trying to find out if there's an asteroid with our name on it. So I'm a little worried about that.
So like Elon.
So what else you can do is you can, and there are coordinated groups that invest this effort. There are asteroids where we don't know how big they are. Okay? We don't have good sort of radar to asteroids.
Right.
So if we think an asteroid is going to come in front of a star and blot out its light, and you have people lined up on Earth to watch this, because how big are asteroids? There's 100 meters across, a few kilometers across, mile across, whatever. It's not thousands of miles across.
Right.
So you line people up on Earth, and some will not see the light of the star dim.
Right.
And other people will.
Yeah.
On each side. So only a narrow path of people will see the light dim. And that can tell you the size of the asteroid. But there are not enough amateur astronomers to do this. So everybody's got to line up, watch the object, keep good time, and do this. So yes, there's still things to do. But also, we have this citizen science projects. We're awash in data.
Yes.
And we say, we're looking for this, help us. I mean, we might put AI on it, but sometimes the human touch matters. And because not all AI is human yet. And so, yes, there are ways you can still contribute.
Very cool. There you go. All right. This is Sharahi Ravi, who says, greetings, Dr. Tyson, Lord Nice. Currently reside in Dubai, United Arab Emirates. I am a researcher and a graduate student in astrophysics. What possible aspects of our current model of the Big Bang Theory do you feel will be revised, considering the contradictions to the same by the latest James Webb Space Telescope observations?
Yeah, so the Big Bang is supported by so many different lines of evidence that if our galaxy models don't match what we see, chances are it's a problem with the galaxy models.
It's the models.
Yeah.
Right. Not the Big Bang itself.
Not the Big Bang itself.
It's the way we've modeled
galaxies are embedded within a much larger matrix of observations and data that have been affirmed by measurements over decades. So we think we understand galaxies. The whole point of the James Webb Telescope was to observe galaxies being born.
Right.
Because we don't fully understand that process. If we take what we think galaxies should be like and they don't match it, you don't say toss out the whole Big Bang. You say maybe our understanding of galaxies is flawed.
There you go.
But saying our understanding of galaxies is flawed is very different clickbait from We need to rethink the Big Bang.
Right.
And so that's what we're all caught up in here.
Exactly. Okay.
It's clickbait.
Right. That's it.
That's what do you expect?
Yeah, exactly. And Yes King says, hello, Dr. Tyson, Lord Nice. Yes King of Queens here in New York. If we ever get to move to Mars, will we be stronger and faster because we're accustomed to Earth's gravity like John Carter of Mars? So are we stronger on Mars? There's the real question.
Yeah.
When we get there.
That's an odd question to answer. Because the question is, are you stronger than what?
Right.
Okay. If two of y'all go from Earth to Mars, whatever your strength ratio was here on Earth,
it's going to be that
it's going to be that on Mars. If somebody can kick your ass on Earth, they're going to kick
You're just getting a Martian ass whooping.
I'm just saying, in terms of strength. So we have to be precise about how we're going to answer that.
Right.
Okay.
How much stronger will I be as an individual once I land on Mars?
All right. So we got to benchmark it. So let's say on Earth, you can lift 100 pounds.
Okay.
Okay. We have to ask, what does that 100 pounds weigh on Mars? Weighs 40 pounds.
Right.
So on Mars, you can lift more than your 100 pounds.
Right.
Because it doesn't weigh as much, not because you're stronger.
Exactly.
Yeah. I'm just am I clear about that?
Oh, absolutely. Yeah. So I'm getting that 220 pounds that I'm lifting, but it doesn't make a difference because it's really still 100 pounds.
Well, on Earth, it's 100 pounds.
Right. It's still 100
pounds. So
pounds.
you are not actually stronger if everything you're lifting weighs less.
But the stuff that I bring from Earth to Mars, which probably won't be a lot because the truth of the matter is you're going to print everything that ideally you're going to print.
In situ resource utilization.
Ooh, I love it.
ISRU.
ISRU.
Yeah, it's a whole branch of NASA.
In situ resource utilization.
In situ, getting all Latin on you
yes,
there. Okay.
Exactly.
So they don't want
in the situation.
They don't want to have to carry everything.
Right.
Because that's very costly for the payload of any rocket.
Right.
We did a rocket equation explainer one time.
Yes, we did.
How quickly you need more and more and more fuel to carry the fuel that you haven't burned yet to carry the excess payload that you're trying to take.
Right.
So if that's what it is, then you would be 3D printing it on Mars. Using raw materials there.
Absolutely.
Yeah.
So now, let's just say I need an object, and here on Earth it weighs 200 pounds, and there on Mars, when I print it, it's going to be the same, like 200 pounds, but it won't be. It'll be Martian, much less.
Well, it'll be Martian weight.
It'll be Martian weight.
80 pounds.
80 pounds.
Okay.
And so I'm going to be able to...
I do that right?
Yeah, 80 pounds, because 100 is 40. So it's going to be 80 pounds on Mars, and so really it doesn't make a difference.
So here's something that matters.
Okay.
If you're going to build something,
right,
structurally, it doesn't weigh as much on the supports.
Okay.
So you can build
bigger, stronger structures.
Bigger structures in lower gravity than you can here on Earth.
Cool.
Yeah.
All right.
And anytime gravity is less, you can do more.
Right.
So look what our mammal branch of the tree of life has done when we entered the water. When we entered the water, but how much do you weigh in water?
I don't know.
Zero.
Nothing.
You're neutrally buoyant.
Right.
You'll slowly sink or you'll slowly float.
Right.
But basically, because humans, depending on how much fat to muscle density you have,
let's not talk about that.
Okay.
Please.
But some will sink and some will float. So on average, we are the same density of water as we are of water. So in water, we don't weigh anything. Okay? Put a scale in water and stand on it and read it. Okay? That's what I'm saying. Okay. So when you don't weigh anything, then structurally, you're not putting yourself at risk. And that's why the largest creature there ever was is a mammal, and it lives in the ocean.
Right.
It's a whale.
Right.
The blue whale.
That's it.
We got one of those hanging in
the museum.
In the museum.
Yes.
So when they say, how much does a whale weigh?
Right.
The answer is 0. They give you a weight. And how do they give you a weight? They take it out of the water.
Right.
Put it on a scale on dry land.
Right.
And then it weighs, gazillion tons, but that's not the weight that the whale feels as it moves through the ocean.
There you go.
Now, there's another side of this, not to just make a long answer longer, but your weight is whatever is the attraction of gravity is to you, okay? Your mass doesn't change.
Doesn't change. Right.
Doesn't change.
Right.
Okay? Mass is count up the molecules in your hand, in
Right.
your body, in
Right.
the rock. The mass is the mass. The measurement of a mass is the same no matter where it is in the universe.
Okay.
Okay?
Nice. All right.
Wait, unless it's moving relativistic speeds, then the mass increases. But holding that aside,
Right.
that's a different conversation.
Okay.
Okay? But mass matters with regard to momentum.
Right.
Okay, so watch. If I take a 100-pound brick and I throw it at you,
I'm suing you.
it'll knock you over.
Yes, it will.
Okay? Now, so how much mass is in the 100-pound brick, we can ask.
Right.
Okay? You can measure up that mass. If I pick up that brick on Mars, it only weighs 40 pounds. But if I throw it at you,
The mass is the same.
the mass is the same.
Right.
It'll knock you over in exactly the same way it would have done it here on Earth.
Right.
All right, next question.
All right. This is Alicia Okoroafu. If the Earth center wasn't hot and there was a hole all the way through, what would happen if you jumped in? Because you will only fall down until the center of the Earth, and then you'll start going up and you'll start falling backwards. Oh, by the way, my name is Arian, age 11, and I'm from United Kingdom, Wales. Okay.
Wait, so what was the first name? That's just a handle?
I guess that's mom or whoever who sent it. So this is what Arian wants to know. What happens when you jump in a hole that goes all the way through the center of the Earth?
Oh, yeah. So I'd like the fact that Arian turned off the heat first.
Isn't that something?
That's good. Very
Arian knew the
thoughtful.
deal. She was just like, we have a molten core.
Yeah.
So at the center, here's what happens.
Right.
Yeah.
You got it. So,
Crackle sizzle.
yeah, the core is hot enough to vaporize you, so you would not make it to the other side, just so you know. But if you dug a hole through, and I did this, I mean, I didn't do it. I did the math on it.
Mm-hmm.
Well, when I was a kid, maybe when I was 11, I said, if you dug a hole from the United States, because
Right.
that's where I lived,
Right.
where would you come out on the other side? And everyone says, if you dig a hole all the way to China.
Right. That's
Okay.
always the case.
That's how
You
we
dig
say
a
it
hole to China.
here in the United States.
That's right.
However, China is not where you will land if you dig a hole through the center of the Earth. Because if you dig a hole through the center and you start in the northern hemisphere, you have to end up in the
southern
in the
hemisphere.
southern hemisphere.
Right.
If you start in the western hemisphere, you got to end up in the
Eastern hemisphere.
that's how the geometry works.
Is that because it's a ball?
It's a ball.
Right.
All right. So when I did that and did the measurements on that, if you dug that hole from the United States, you would end up in the Indian Ocean. So we have to ask now where, if you live in Wales,
Right.
where does their hole come out? Well, it's easy to figure that out. It's trivial. Okay. Because what line goes through the United Kingdom?
The
It's the most
prime
famous line,
meridian.
the prime meridian, most
Prime
famous
meridian,
line in the
right.
world. And what is diametrically opposite the prime meridian?
The equator. What?
Let's try that again. What's diametrically opposite the prime meridian?
Oh, give me a second. I'm trying to think of the line that goes across the North Pole,
And down on the other side.
On the other side.
It goes all the way through.
the South Pole.
No, okay, I'll help you.
Oh, the prime meridian.
No, the prime meridian is
It's
only
only-
pole to pole, but on the
Pole.
other side we call it what? It's the same line continue, but we have a different word for it on the other side.
Oh, I don't know.
The international date line.
Oh, I didn't know that. I have never made that connection. I've always, because people always talk about the international date
In
line
its own world,
in its
in its own
own
way.
world.
Okay.
And then they talk about the prime meridian because it's like, oh, this is the line that runs
Okay.
all the way through. So I didn't know that.
Okay.
Okay, cool.
All
Okay.
right.
So that's why
When I was a
just
kid, I
like,
spent a lot of time looking at maps and globes and stuff. I thought that was just cool. But just to be clear, I was bigger than other kids. So
Thank God.
that kind of nerd activity
let me just tell you something.
get your ass whooping.
I'm just gonna say.
Up in the Bronx.
Yes.
But
You're a man of large stature. If you were Chuck Nice size, the world would not have Neil deGrasse Tyson.
so what's convenient about the international date line, because that goes through Greenwich, England,
Right.
all right, is on the other side is the middle of the freaking Pacific Ocean.
Right.
So you don't want the international date line going right in the middle of your country.
Right.
Because then one half the country would be one day, the other half would be the other
other
day, 24 hours different, right?
Exactly.
And so you don't want that. So it's just convenient. Now, there's few places, is it the Solomon Islands? There's some place where they had to do some bending.
Right.
Because there's some scattered islands in the Pacific.
Right.
But basically, it bypassed that challenge.
Right.
Okay? Just thought I'd say that. All right.
Okay.
So Arian will dig a hole and will land in the South Pacific.
Okay.
Okay. Let's get back to the question.
What's going to happen when you jump in?
Yeah, so you jump in, you will fall and accelerate continually.
Right. You're picking up speed the whole time.
Actually, it's not discrete, so I have to say you will fall and accelerate continuously.
Right.
The difference between continual and continuous. I was talking to a Brit who invented the language, so we got to be good about the language here.
Yeah.
Okay.
That's right.
So you'll jump in, you'll accelerate continually until you get to the center. Let me just, for those who didn't know, okay, a river flows by continuously.
Right.
The parade floats moved by
Continually. Right.
Right, because those are discrete objects.
They're discrete and they are not connected.
They're not connected.
But if it's connected, then it's continuous.
And usually it's the same material substance.
Correct.
Right?
Okay.
You can't tie a chain between the floats and call it continuous.
Right. Exactly.
No. So you jump in, you will accelerate until you get to the center, where you'll hit peak speed.
Nice.
Peak speed. And I'm thinking that speed is 5 miles per second.
Okay.
I have to verify that. I'm just pulling that out.
5 miles per second. So you're dead.
You are weightless.
Right.
You don't care that you move 5 miles per second. Well, you care.
That is true.
You're on Earth going 20 miles per second around the sun.
So now, okay, I'm going to let you finish because
your speed, you don't care what this.
No, I was
when
talking
you're
about
in an airplane,
when you said peak speed. That means now we're going up because you're.
I didn't get there yet. We're in the center of the Earth.
All right.
Okay,
that's what I'm saying.
Peak speed, center of the Earth. Now, what happens to you? The hole is all the way through the Earth. You will overshoot the middle.
Okay.
Right. You're going 5 miles per second. You'll overshoot.
Right.
You'll overshoot the middle, and now Earth will slowly slow you down.
So that's what I was saying. You're dead. So that breaking, actually, you're going up now.
You're not going up. Up is any way away from the center of the Earth.
Exactly.
Right. Okay.
So you're going up in terms of.
Now you're going up into and towards the South Pacific if you're in Wales.
Right.
Okay. And you're slowing down continuously.
Right.
And in the exact rate that you had sped up going in. So it's the exact undoing of everything that happened en route to the center of the Earth.
Sweet.
So then you will we're ignoring air resistance here, of course.
Okay.
Okay.
There we go.
And then you get to the South Pacific. Now, assuming the water's not just flowing in against you.
We have a tube that takes us above.
We'll give you a life-saving tube.
Right.
You'll come right up to the edge, and unless somebody grabs you, you're going to fall back down, and you're going to repeat this forever.
Oh, that's terrible.
Somebody's got to grab you.
Oh, this is a good version of hell.
You'll just keep going back and forth.
Right. Like,
there it is.
Oh, well, that was cool.
And one round trip,
right,
it comes back to Wales, one round trip takes the same amount of time as an orbiting spacecraft.
That's really cool.
It's really cool.
Yeah, because you're going the diameter of the Earth.
Well, you have to do the math and the Newtonian physics, and it all works out.
Yeah, it makes sense, though, because you're falling, it's falling.
Yes.
So you're falling the diameter, it's falling the circumference.
You're both in free fall.
That's awesome.
In Earth.
All right, here we go. Brett S. Chapel says, hello, Dr. Tyson and his niceness. Warm greetings from Copenhagen.
By the way, one of the most famous astronomers ever was Danish.
Okay.
And I sat for 20 minutes with some native Danes to teach me how to pronounce his name.
Okay.
And I will show off now that I can pronounce his name.
Okay, who is this?
Tycho Brahe. Tycho Brahe, we call him.
Oh,
here.
Tycho Brahe.
Tycho.
Okay.
There's a crater on the moon named after him called Tycho.
Tycho.
It's the crater that has rays coming off of it.
Nice.
Yeah, it's called the ray crater Tycho. Very famous crater. But Tycho Brahe.
Tycho Brahe.
Yeah, I want A+ for that because I worked my butt off pronouncing that.
Pretty cool.
Okay, what do you have?
All right. Carl Sagan edited a golden record, which went into space in 1977 on NASA's Voyager expedition. This disc included music by diverse sources such as Chuck Berry, Peruvian panpipes, and Johannes Bach. If you had to revamp the playlist to meet 2024 standards, which one of the two songs would you add to ensure a more modern repertoire?
Oh.
So is there a song recently? So let's get past Chuck Berry time. So I'm going to say you have to go from late 60s till now, what 2 songs would you add?
Two
to
songs.
Two songs.
Two songs.
They said. From late 60s till now. Because Chuck Berry's the 50s.
Okay.
So you got to go late 60s till now.
I got to put in Rapper's Delight.
Well, it did start it all.
It birthed
an entire
it's
genre.
from my home borough, the Bronx.
That's true.
Okay. Bronx birthed hip hop.
Well, there you go.
So I put in Rapper's Delight.
Wow.
Okay.
Worst rap song ever made. But the most important rap song ever made.
And it charted. It was #1.
Yes, it did.
And we danced our ass off in college
This
to
is
that.
true.
Because when it came out when I was in college.
All right.
And
All right.
what would be fun if we put John Cage's 427 or whatever the name of his work is. You know, it's a piano work.
Oh, okay.
You know it?
I don't think I know that.
The pianist sits there at the piano and doesn't do
Is
anything.
this the guy who doesn't play?
Doesn't do anything for 4 minutes.
Okay, right. I've heard about this. Yeah.
We should put that on the record. I might have thrown in a disco song, but disco kind of came and left.
Yeah.
And I would not have predicted that at the time.
Right.
I would have said hip hop was a flash in the pan and disco would be here forever.
No.
But the opposite has happened. Yeah.
Yeah.
So what 2 songs did you pick?
Okay, for me, I'm going to go Kendrick Lamar, They Not Like Us.
Oh.
Yeah.
Ooh.
Just because clearly these are aliens that found it.
All right.
And for my second song, Smells Like Teen Spirit, and that is Nirvana. And the reason is because I don't know any teenager ever, no matter what their color, no matter what their creed, no matter like what their background, who doesn't hear that song and isn't moved by it. They truly capture teenage angst in a song.
They found the resonant frequency
Way to say it.
of not just of a generation, but of
a period of life.
life.
Yeah, a period of life. Everybody knows what it is to have the anxiety of teenage existence, and it exists in that song.
All right.
So yeah, it smells like Teen Spirit. Yeah.
All right.
Yeah.
All right.
So
I
there
love
you
that.
go.
Okay, we hope that. There you go.
All right. Well, there you go. This is Oliver Cook. Hello there. This is Oliver. I'm a 36-year-old painter and decorator from South Wales.
Whoa.
Love the podcast.
This is a second
This
question
is another
from Wales?
second from Wales. I want to know if there's such a thing as absolute stillness in the universe. And if so, what would happen if we were to reach it? Would everything else just blink out of existence? Wow, look at that.
That'd be a fun science fiction premise.
That would be.
Or if you can't find it, you create it.
Right.
Right? Earth is rotating. Let's stop the rotation.
Right.
Earth is going around the sun. Let's stop that. Or the sun is going around the galaxy. Let's stop that.
Right.
Galaxy is falling towards it. Let's stop
The
that.
power of stillness. What a cool super. I have the power. And now, would that be stillness all the way down to the vibration of molecules and atoms?
That's not how I'm thinking of the question.
Okay.
But it turns out that that's not possible because quantum physics demands that even when you cool something down
Right.
to absolute zero,
Absolute zero.
in the day,
Right.
in Lord Kelvin's day,
Right.
his actual name was Thomson, but Kelvin, when he became Lord, he was Lord Kelvin.
Right.
A brilliant physicist, a little cocky, but brilliant. He pioneered the Kelvin temperature scale,
Right.
which is the absolute temperature
zero.
scale.
Right. That's
So what they found was, at any given temperature, air molecules are vibrating.
Right.
Or they're moving among and bouncing off each other.
Okay.
If you drop the temperature, they move a little slower.
Right.
Drop it some more, they move a little slower.
Nice.
And so he extrapolates it. There must be a point where they stop moving at all.
Okay.
If they stop moving at all, there's no temperature left. Absolute zero.
Nice.
You can't have temperature less than the temperature of something not moving.
Ooh.
Completely reasonable before quantum physics.
Aha.
Quantum physics says you try to take it to the lowest possible energy state, and you cannot characterize a zero energy state. There's always some fluctuation.
Something is moving.
Fluctuating.
Or fluctuating or
I want
doing
to distinguish sort of vibration from translational movement.
Exactly.
And I'm thinking he means translational movement. Is there a point where nothing is moving?
Right.
Okay? So, the answer is no.
Wow.
Because you've been on a train before.
So true.
Let's say Amtrak, not everyone has it, but Europe, they're all about trains.
Right.
Here, some of us have been on trains.
Yeah, we only have one. It's called Amtrak.
Yeah. And
Yeah.
you sit on the train and you look out the window, and all of a sudden, things start moving.
Right.
You're at the station,
Right.
and you're there,
Right.
and then things start moving backwards.
Right.
And you rationally say, oh, they're not actually moving. I'm moving because I'm on the train.
Right.
But you didn't know that because it was so smooth.
Right.
Okay? All I'm saying is, if you believe you are stationary, someone else has equal rights to that claim. And if you say they're in motion, they can legitimately say, no, I'm stationary and you're in motion. There's no experiment you can conduct to say otherwise.
I know I am, but what about you? But what am I?
I know I am, but what are you? So that is a foundational principle of relativity.
Right. Yeah.
Okay. And so we're stuck with it. That's how the universe is put together. There was a brief moment where, looking out to the cosmic microwave background,
right,
the question was, is it a different temperature in this direction than that direction?
Okay.
Because if it is,
right,
that means we can tell absolutely that we are moving relative to a reference frame that's the entire freaking universe.
Right.
There is no such thing as no motion.
There's no such thing as no motion.
Correct.
Because once you get down to the quantum, there's something.
And even so, even if you think you're in motion,
someone else's frame of reference.
It's a reference frame.
Someone else's frame of reference
even
says,
if you think you're not
they're
moving,
in motion. Your frame of reference says, I'm in motion. You're still.
Correct.
There you go.
And there's no experiment that you can conduct that can tell you differently.
Right.
Okay.
All right, here it is. Caleb Carter says, howdy from northern Indiana. I just watched an episode where someone asked if a pair of quarks get spaghettified, would they sooner or later find an equilibrium? Y'all responded with essentially, I don't know. But I do know. This is the moment there is enough energy to sufficiently separate them. They would just make quarks to become a pair again. Thus, an infinite amount of quarks would be made. I remember y'all talking about how a single H2O molecule doesn't make water, but water is made from clumps of H2O. It's possible that quarks and gravity are related in a similar way. If, and this is a mighty big if, both cases are true. Could this explain why black holes are infinitely dense? Could this just be another version of a runaway thermonuclear reaction like we see in stars, but in terms of gravity?
I'm thinking again about this quark falling into the
black hole, which
would it
we were talking about.
Would you have a runaway creation of quarks? And I realized, where's it getting its energy from? It's getting its energy from the gravitational field of the black hole.
Correct. Right.
So the black hole, I think, would eat itself.
It's right.
Its entire gravitational field would morph into particles.
So you have this kind of just infinite loop that would keep happening, and it could end up eating itself.
So
that's really cool.
Now I'm no less than what I knew before.
Exactly, right.
So I don't have a good answer. Yeah. I don't know how to respond.
Right.
It remains a mystery, at least to me, if not to others.
Okay.
Out there.
There you go.
Mm-hmm.
Fabio later says, good day, Fabio here from Washington.
Fabio?
Yes, Fabio. All right, he says, in your educated opinion, do you think media censorship should exist in future space colonies in order to mitigate most of humanity's undesirable traits? Wow, bro.
That's a good one.
Wow, look at you.
Yeah, I mean,
he's talking selective, protective censorship is what he's talking about.
With all of its weaknesses, I think its greatest strengths outweigh them, and that's the strength of freedom of speech.
There you go, my friend.
And maybe I say that because I'm indoctrinated as such as an American.
I'll tell you why you say it, because you live in the greatest damn country on this face of this earth, America.
So, and maybe because I'm indoctrinated that way, I allow that to be a possibility.
First of all, I agree, but I disagree that it's indoctrination. Here's why I disagree that it's indoctrination. Because with the right to censorship comes a certain power, and we all know that power corrupts.
Yes.
Power also seeks power.
Yes.
And so if you were to give people the ability to censorship, it never ends well. Okay. That's all there is to it.
It's not just indoctrination, there's evidence.
There's empirical.
If you want the stability of that colony to be a thing.
Right.
Like with all the challenges and all the fits and starts that free speech causes,
right?
The benefits outweigh
any of the detriments. Yeah. And quite frankly, what you need to do, Fabio, is have free speech and teach everyone in that colony to think critically so that they can assess the value of the free speech that's being spoken.
Ooh, so you get it. You nip that in the bud.
That's it.
You start out that way. Maybe you don't even allow people to go to that colony.
Right.
Unless
they can think critically.
We can formalize this. We should name that planet Rationalia.
Okay.
Okay?
Like in your book.
Which I just happen to have.
Excellent.
So I
Wait,
tweeted.
you got to tell them the name of the book.
Oh, Starry Messenger, Cosmic Perspectives on Civilization.
Sweet.
So I and others came up with this idea of Rationalia at a conference.
Okay.
A science conference.
All right.
And I tweeted it. It says, Earth needs a virtual country. I wasn't thinking other planets.
Right.
Virtual country, Rationalia, with a one-line constitution. All policy shall be based on the weight of evidence.
Whoa. There you go. Boom. That's it.
That's it.
That's it. You get rid of so many problems that way.
So many problems.
So
and
many
if you don't have
problems.
evidence, then there's no policy.
Yeah, exactly.
Just to be clear.
Go ahead.
On Rationalia, you can have feelings.
No, your feelings are fine, but you can't.
You just can't make a law.
Right. You can't write.
You just can't write a law.
You can't be a part of the conversation.
No, you can have a conversation. You just can't write a law based on your feelings.
No, but that's what I'm saying. When we are debating the law, what the law should be, your feelings don't matter because it's all about evidence.
If it's about evidence, correct.
Right.
Correct.
Yeah.
So on that planet, free speech would be, oh my gosh.
Exactly.
It would be the blooming of the greatest democracy the universe has ever seen.
There you go. Wow.
So that's from the chapter in here called Law and Order.
Law and Order.
Law and Order.
From Starry Messenger.
It's things that we care deeply about in civilization. It's what they look like when seen through the lens of science.
Right.
And so many of the arguments that we have over holiday dinners, they evaporate.
Right.
In the presence of rational analysis.
There you go.
So that's what goes on there. Okay.
Hello, Dr. Tyson and Lord Nice and anyone else that might have been invited. Craig Cordwell from the UK here. I was wondering, how sure are we that spiral galaxies like our own and our neighbors, Andromeda, are not being sucked into the black hole, which is what causes the flushing toilet-like shape that makes up the galaxies? Love the show and look forward to hearing the episode.
Ooh, okay. This makes like 4 people from the UK. What is that on this round?
Yeah,
okay.
we got a lot of people, a lot of love from the UK.
A lot of love. So black holes are not giant sucking machines.
Right.
They just have a gravitational field.
Gotcha.
If you get really, really close, kiss your ass goodbye.
Right.
If you're not, you'll just maintain an orbit around it.
Like we do the sun.
Like we do the sun. Exactly as we do the sun.
Right. We don't crash into the sun. We're not getting sucked into the sun.
Right. And so if you step back, it looks like all the planets are spiraling around, which they are.
Right.
But they're not getting sucked into the sun. Right. All right. So the toilet bowl effect.
That's swirl.
These are called spiral arms. And our understanding of them came of age while I was in graduate school. Because how do you maintain that? And because the inner parts of the galaxy actually will complete an orbit faster than the outer parts. So you get this stretching of these coherent cloud formations, gas form. They're not cloud.
Right.
They're gas clouds,
not puffy clouds.
Not puffy Earth clouds. Right. They're gas streams of gas that, because the galaxy rotates, as we say, differentially, which means the inner parts rotate faster than the outer parts. It will drag it into this spiral shape.
Right.
And one of our big challenges was, how does it maintain the grand design 2-arm spiral without over time just winding up on itself?
Right.
Okay, so that's where it got complicated. And we had to worry about what's called spiral density waves. It's not really a physical gaseous structure. The gas is everywhere. There's a density wave that's moving across the clouds, triggering star formation.
Wow.
So wherever this density wave is, there's star formation in that shape. So it's more complicated than it looks, but all I'm saying is everything is just simply orbiting the center of the galaxy.
Right.
And it's not like a toilet bowl that's ultimately going to go down the tube.
Right. And because there's gravity at the center of the galaxy.
Yeah, there's gravity there, and that's what maintains the orbits.
The orbits.
Right. But if you want it to fall in, you're going to have to stop the motion.
Right.
Then it won't know to go sideways, and it'll just fall straight in.
Straight
But
in.
that's what you'd have to do if you wanted it to actually behave like a toilet bowl. By the way, we detect black holes because of this toilet bowl phenomenon.
Oh.
Okay? If a gas cloud or star gets too close, tidal forces will rip it apart. The material spirals around, and the spiraling material, because the inner parts are rotating faster than the outer parts, there's friction. And wherever you have friction, you have what?
Heat.
Heat. So this, which we call an accretion disk,
Right.
this disk, as it spirals, gets hotter and hotter and hotter and hotter and hotter. It starts glowing. First red hot, then white hot, then blue hot. Then it's glowing so hot, it emits X-rays.
Aha.
That's how hot it gets. And so our greatest discoveries of black holes occurred when we launched X-ray telescopes into orbit,
Right.
Earth orbit. And you look out and you see these sources of X-rays. Those are black holes talking to us in the universe.
Is that the Chandra?
Yeah, Chandrasekhar, a brilliant Indian physicist. We named the telescope after him. In the way we named Hubble after Edwin Hubble.
Right.
So the Chandrasekhar X-ray telescope is named after him. Right.
Cool, man.
But anyway, that's how we found black holes. Very cool.
There you go.
And that is a toilet bowl because it's falling in as it radiates away.
Cool.
Whereas we are not falling in. It's just a density wave moving across clouds that are already there.
All right, here we go. Hello, Dr. Tyson, Lord Nice. This is Sarah coming from Austin, Texas. When we're talking about the age of the universe, 13.8 billion years, is the age of years in Earth years? Or is it the average time used? If it's Earth years, then wouldn't it be a different age of the universe depending on your location?
Yeah, it's Earth years.
It's Earth years.
That's not a unit of time we just all agree to.
Right.
And that exists as a unit of time right now, with or without the Earth.
Right.
We've defined it as a length of time measured by an atomic clock.
Right.
So if Earth got destroyed out of the solar system by some cosmic monster, a day and an Earth would still be defined.
Okay.
Because we no longer rely on the rotation of the Earth.
It's not the rotation.
And the orbit of the Earth around the sun
Right.
to reckon our accounting of seconds.
It's a standard unit of measurement.
Correct.
Okay.
So, yeah, it's just Earth years.
The same as inches and centimeters.
Yeah,
You know
you
what I
pick
mean?
a unit,
You pick
and
a
that's what it
unit,
is.
and that's what it is.
And
So-
you will get a bigger number in centimeters than you will in inches.
Right.
That doesn't mean the distance
But
is
the
farther.
distance is the same. You're just
Same.
measuring it in different terms. So it doesn't make a difference.
Correct, yeah. So nothing to lose sleep over that. All right,
Okay.
what else you got?
This is Nobody. Hey, Nobody from nowhere, Vermont. Hello, Dr. Tyson, Lord
By the way,
Nice.
there's a character in West Side Story called Anybody. Anybody.
I did not know that.
Yes. It's a tomboy called Anybody.
Oh, really?
Yes. She wants to be with the gang.
Oh,
She got dirty face, short hair, wears pants, can fight, but they don't let
sounds rather sexy to me
her. They didn't let her in because
because she's a girl.
she's a girl. I'm just wondering if anybody's came from nowhere.
Oh, okay. So there you go. If anybody came from nowhere.
This person's from nowhere.
Nowhere.
right?
He's from nowhere, Vermont.
Nowhere, Vermont. Okay.
So he says, hello, Dr. Tyson and Lord Nice. Is there any way for a non-physicist to correspond with a physicist about their papers without being a bother?
So almost every academic
Right.
on their university page
Right.
has their email
Right.
posted.
That's right.
Practically everyone. What you want to do if you want to correspond, if probably you have an idea, would you do some homework first?
Make sure.
Do some homework.
Right.
Don't go to them and say, I have an idea that Einstein is wrong and that all of you don't know what you're doing.
Right.
Listen to me.
Yes. And there are those out there.
Because you spent 2 hours watching a YouTube video.
Exactly.
And this person spent their life and career studying that one subject.
Exactly.
Okay?
Yes.
So just do a little homework.
Do a little homework. Now,
Okay.
here's the thing. Correspond without being a bother.
Oh, without being bothered. Do your homework and
your
ask
homework.
an intelligent question.
Okay.
And don't tell them that you have a new secret to the universe and they have to listen to you. Otherwise, no, that is not humble. That is rather arrogant. That you, a non-professional, would know something more than the professional. So come to them a little more humbly. I have an idea.
Right.
It might be correct. I've thought about it in this way.
Right.
What do you think of it? And don't send them 20 pages. They won't have time for that. Okay?
Exactly.
And do your homework. Learn, buy some physics books.
Yes.
Learn
Right.
some physics.
Right. This is
All right, what else you got?
This is Mitchell Adkins, and Mitchell says, "Hello, Doctor and Lord. Well, we're getting shorter and shorter, aren't we?
Mm-hmm.
This is Mitchell from Cincinnati, Ohio. I heard an old episode of yours where you talked about the spaghettification of particles at a black hole. You said that this continues all the way down until everything is ripped apart, which would make sense. However, quarks are held together with asymptotic freedom, meaning that the strong force holding them together increases the further you pull them apart. Would there theoretically be a point where the gravity ripping quarks apart would balance the strong force of asymptotic freedom and actually end up balancing and creating some kind of equilibrium?
Okay. We've never seen an isolated quark.
Oh.
They come in pairs.
Okay.
Pairs or more.
There you go.
Okay. So let's try to create an isolated quark.
Okay.
Quark. So you go down there and you get a quark pair and they're stuck together.
Mm-hmm.
You begin to pull them apart. And the force holding them together gets stronger the more you pull.
Yeah.
The greater is their distance, the stronger is the force.
Wow.
No, it's not that mysterious.
Right.
Name something every day for which that happens.
Magnets? No.
No, they get weaker.
In opposite.
They get weaker.
Something that you pull apart and it
gets
gets
stronger. Yes.
That happens every day.
You get it every day.
Every day as you pull it apart and it gets stronger.
Ding, 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 ding,
The absence from my children.
No, a rubber band.
Oh.
You pull it harder, it's
and
a stronger
it creates
force.
more tension.
And the closer you're in, the less force there is.
Right.
And a spring.
Right.
Okay?
A spring. There you go.
Right. And mathematically, you can represent that with a very tidy formula. And the spring is what's called a spring constant. It tells you how tight it is.
Okay.
You know, how much energy that takes. So we think of this as a spring. But here's the catch. As you pull them so much apart, at the moment it snaps,
right,
you have pumped so much energy into
pulling it apart,
that energy in that instant becomes two more quarks, and now you have two pairs of two quarks.
Yo.
It's diabolical.
That is crazy.
It's diabolical.
That is crazy.
It's diabolical.
So the energy that you
because it takes energy
separating the quark
equals MC squared.
Right.
Right at the moment, there's enough energy for each one
to create another quark.
It snaps.
And now once again, you got two.
You got two quarks.
You got hydra quark. Nice.
You got two quarks on each one.
Right.
Right. So quarks are diabolical in this way.
That's
okay. So he knows that as you're falling down, the tidal force is going to stretch you.
Right.
That's giving energy to the quark.
Right.
So he's wondering if there's some balance point down in there.
But now, here's the thing, though. As the quark gets pulled apart, okay, what happens is there is a point of breaking. So wouldn't you just start making infinite quarks?
It kind of seems that way.
Because
Chuck.
That's really, forget the equilibrium. We're not looking at equilibrium. We're talking about the creation of the quark. So what you would have is two quarks. Four quarks. Eight quarks. It would just keep going because it would continually.
And the quarks would take over the universe.
That's it.
Ooh. Damn. So what we do know is there is no known force that can resist the gravitational collapse to a singularity.
Right. At some point, the immovable force whatever it's called. You know what I'm saying. What is it?
Movable object.
The movable
irresistible
object,
force.
It meets the irresistible force.
So I don't have a good answer.
Wow.
It seems to me you would have a quark runaway.
Right. That's really.
I got to talk to some people about this.
That's just freaky.
I got to talk to some people about this.
Freaky, man.
I don't have a good answer for you.
Yeah.
Chuck just said the quarks will take over the universe, and I don't have a good rebuttal for that.
Yeah, that's so cool, though. I mean, what a great thing to think about. All right, here we go.
Yeah.
This is Bobden. Bobdan or Bobden, okay? A black hole is matter, energy, and radiation, all compressed down to a point of singularity where space and time cease to exist. On the flip side, a Big Bang is also a point of singularity that explodes matter, energy, and radiation out into a new space-time universe. So why are the origins of Big Bangs and universes still a mystery? It seems logical that the Big Bang births a new universe. Space-times are simply black holes of other universes and space-times. Mystery solved. Right?
Yes.
There you go.
Okay, next question.
There we go. Bob Dan.
So back on my shelf, I got a book by Stephen Hawking. Is the large-scale structure of space-time.
Okay.
It's got some title like that.
All right.
And in it, it describes the physics and the mathematics inside the black hole.
Okay.
And as you go through, it basically opens up an entire space-time. So inside a black hole is effectively a whole other universe, which leads us to wonder whether our universe is
just
inside
of somebody else's black hole.
Somebody else's black hole, correct.
Look at that.
And we have a horizon that you can't get out of.
Right.
And there's stuff beyond it, but you can't see it. So there are some strong similarities between thinking of the universe as a black hole and a black hole as a universe.
Right.
Ooh, that's poetic.
I like it. That's very cool.
All right.
And this is Colin Brum. Will a photon, from its frame of reference, be able to reach galaxies beyond our event horizon should a photon see time stop for the rest of the universe at the speed of light and therefore not experience, listen, the expansion of the universe along which it is traveling?
Damn,
people are getting,
They're going
in.
Going all in.
I'm telling you, bringing up a lot of stuff here. That's a layered question.
All right. So we have to be careful here.
Right.
We will never see the photon exit the universe. That's the whole point of this, what's going on here. The photon will move away, and it gets swept up by the expansion of the universe, and the energy coming back towards us against the expansion of the universe gets diluted until it disappears entirely.
Okay.
At that point, it's beyond our horizon. We can't see it. All right. As far as the photon is concerned, it's just happily doing its thing.
There. Right.
It's just, it doesn't even know.
It has no idea.
No idea.
It's just happily being.
That's like the famous question with Albert Einstein said, if you're in a car driving the speed of light and you turn on the headlights, what would you see?
Right.
Okay. Well, you can't go the speed of light, but let's go 99.9999% the speed of light.
Right.
You do that, you put on your headlights, you see your headlights.
You see headlights because that's it. It's out in
everything
front of
is
you.
relative.
It's at the speed of light. It's relative.
You don't even know you're going at the speed of light.
Exactly.
As far as you're concerned, everybody else is passing you by.
Exactly. Yeah.
Which made the awkward joke I told you when Relativity was published. That was it the New York Times. Somebody made a joke. Hey, Albert, what time does Grand Central Station arrive at the next train?
Right. Right.
So that's the same thing.
That's the same
so
thing.
if you're the photon and you're at the edge, when you're at the edge, that's not your edge.
Right.
When you're at our edge, it's not your edge.
Right.
Any more than a ship going to your horizon. That's not that ship's horizon.
Exactly.
It sees beyond that.
Exactly.
Okay.
Yeah, that makes perfect sense. Right.
Right. And it'll, like I said, and a photon will be absorbed in the same instant it was emitted in its own reference frame.
I love thinking about it like a ship because that's
good.
so
It works
easy
great.
to envision that
Works
you know
great.
that the horizon.
And you know the ocean goes beyond your horizon.
Exactly.
Right.
Right. Unless you're a stupid flat earther, in which case you fall off the edge, you big dummy.
I don't have an issue with flat earthers. I just don't want them to become head of NASA or something
Well,
like
there's
that. Plenty of jobs for them. Okay,
Yes,
if you want to think Earth is flat.
Right. Cleaning toilets is not a bad job. There's a lot of dignity in that as far as I'm concerned. Anyway, this is Tassos Souris, who says, "Greetings, Dr. Tyson. Tassos from Greece here. How would a civilization living in a planet that is surrounded by black holes from all sides perceive the universe? Will we, from the outside, be able to see them? Will they live their own slowed acceleration time frame?" So a couple different questions in there.
So the closer you are to a source of gravity,
Right.
the more time dilated your life becomes.
Right.
So you think you're living a normal life. People from outside see you living more slowly.
Right.
So we will see you living more slowly if those black holes are relatively near.
Right.
That's the first point. Second, if you look out, you will see light bent around black holes. So
Right.
you'll see all these rings,
Right.
these light rings, because that's what the geometry of space-time does when you have a source of gravity and light passes around it. So that's the main difference. The night sky will be these rings.
Yeah.
And Einstein first predicted the existence of rings. They're called Einstein's rings.
Wow.
And then he thought things will never be so perfectly aligned to get a perfect ring that you'll never get a ring. And we get some rings, but generally what happens is if it's exactly aligned, you get a ring. If it's slightly off center, it splits into two parts.
Right.
And then if it's off a little more, you can get 4 parts and then 6. And so, but in the limit of a perfect alignment, you get a ring. And so, yeah. Now, that would be dangerous if you're surrounded by black holes. I don't know how stable that orbit would be.
Right, yeah, exactly.
Yeah.
You're in a pinball machine at that point.
At that point, you know, as they say, there's no such thing as gravity. Your planet sucks. The black holes suck. They'll suck you in.
Right. All right. Very cool. Thanks a lot there, Tassos. This is John Bickford. Says, good day, Dr.
Good
Tyson.
day.
That's what he says.
Very Aussie.
Yeah.
Okay.
John Bickford here from Bolton, Massachusetts. The Big Bang, did it disperse matter in all directions somewhat equally? If so, and the universe is expanding in all directions, what happens in the space where the Big Bang happened? Look at that.
Isaac Newton, my man.
Right.
So Isaac Newton argued that the universe must be infinite after he discovered his laws of gravity.
Right.
Must be infinite. Because if it's not, all the matter will find a center to fall to. And it would all fall to form one great heap of mass. But it's an infinite, then there's no one place is not more special than another.
Right.
Now, he didn't imagine that you can live in an expanding universe.
Right.
That was outside of his worldview.
Yeah.
An expanding universe, you're not all going to fall to one spot because there's a force preventing that.
Okay.
In our case, we call it dark energy. So with that place where the center occurred no longer exists in space. It only exists in time.
Right.
The timeline, if you go back to the beginning of time, on that axis, when you get there, all the matter will be in the same place. You go forward, the expansion of the universe, you don't have access to that point in that space. Gotcha. So I'll give an example. So if you have a balloon and you're inflating the balloon,
right?
You start out, the balloon is like tiny.
Yeah.
Right? That's the Big Bang. Okay? Right. Or the whole balloon is in one spot right there. Now you start blowing on it, it expands away from that spot.
Right.
Is that spot on the surface of the balloon? No. It's in the center of the balloon. How do I get to the center of the balloon? Turn back time. And the balloon gets smaller and smaller and smaller. Now you're back at the center.
Right.
So
you'd have to shrink the universe
by going backwards in time.
Backwards in time.
Exactly. So the center exists, but not in the space coordinate. It exists in the time coordinate.
There you go.
Yeah.
Really?
Deal with it.
Yeah.
We get through a lot of questions today.
We are.
More than usual. Okay.
This is Ilyas Siametis. Ilyas Siametis.
That does not sound right, but we'll go with it.
Yeah.
You can put a little flavor in it.
Okay.
Ilyas.
Yes. Siametis.
Okay. Go.
Dr. Tyson, Lord Nice, Ilyas here from London. Would it be theoretical?
London, Ontario? London, Connecticut? London?
Hey, man, he just says London.
Okay.
So
is there a London, Ontario?
I don't know. All right, so he says, would it be theoretically possible to break the bonds between atoms of something and reconfigure them into something else? Let's say manipulate the billions and billions of carbon atoms in a wooden chair and make a table instead. Strong emphasis on the word theoretically.
Yeah, that's not interesting, though.
Okay.
To turn a wooden chair into a wooden table?
Well,
you're not really manipulating atoms. You're just
reassembling
the macroscopic, the wood.
Right. That's all you're doing is taking the wood and moving it around.
You're moving the wood around.
Right. That's it.
If you want to change molecules, do something fun.
Right.
What you want to do is take your molecules and rearrange them and make an alien.
Right.
That's still alive, but it's not you. It's some other thing.
Right.
Do something interesting. If you're going to have power over molecules and atoms, now what chemists do is, because we don't have tools to pluck atoms and reattach them, we put them in vats of other chemicals that make that
a reaction.
Make a reaction.
Right.
And these are called catalysts.
Right.
Okay. I want this molecule and I got that molecule, put in a catalyst that makes that.
Boom.
Okay. And does that natively and naturally. So that's how we're doing that today.
Okay.
So yeah, do something better than a chair to a table.
Right.
And yeah, but in principle, you can turn it into anything organic.
Right. Yeah.
Because if you can use the molecules of life, that's organic chemistry. Why not make something else organic?
I love the idea. Okay. Well, there you go, my friend.
Yeah.
All right. This is Aaron Turetsky. says, hey, Dr. Tyson, Lord Nice, Aaron here from Staten Island, NYC.
All right.
He says, my question pertains to the way that we visually display Earth in globes, maps, and elsewhere. Since magnetic poles flip and the Earth's landmass are constantly shifting, is there any scientific reason that we decided Antarctica would be at the bottom or the South Pole? I understand that human civilization happens to exist while a majority of the land is in northern hemisphere, so our maps are northern biased. But what does science have to say? For example, if an alien civilization was to look at the Earth through their telescopes, is there any reason they would know that Battery Park is at the bottom of Manhattan and not the top? Wow. My man got a problem with globes.
And plus, he mentioned Battery Park because one way to get to Staten Island is through the Staten Island Ferry,
which
out
is
of
in Battery Park.
So what does science have to say about it? First of all, at the beginning of the film, Happy Feet, where does that take place?
At the
it's penguins, so there's only one place it can take place.
South Pole.
South Pole.
Penguins.
Antarctica.
Antarctica.
The camera moves in on the Earth.
Right.
And of course, North Pole is up and South Pole is down. But this entire movie takes place at the South Pole.
Right.
So as far as they're concerned, that's where the action is. So you know what this movie does? Instead of going down to the South Pole, the entire frame rotates 180 degrees.
Nice.
And you go straight on in to Antarctica.
Okay.
That was a point of view shift.
That's pretty
cool. You know who did that movie? Happy Feet, George Miller, the same guy who did Mad Max.
A little departure.
So scientifically, we use the right hand rule.
Okay.
Okay. So stick out your right hand.
Right.
Open palm open.
Palm open.
Now make a curl your fingers. Keep your thumb up.
Thumb up.
Okay. Any object that's rotating in the universe, if you curl your fingers in the direction it's rotating, your thumb is the North Pole.
That's the North Pole.
Yes. For any object anywhere. Correct.
Okay.
If you want your thumb to stick in the direction of the pole, you have to use your left hand.
Oh, that's okay. So the right hand rule is right hand, thumbs up.
That's how you know what North Pole is. And if you know what North Pole is, you know what South Pole is.
You know where South Pole is. Okay, gotcha.
Okay?
Okay.
Yeah, so yes, of course we are north biased, but there is at least consistency with all maps show north.
Okay.
North up.
All right.
And he mentioned the magnetic pole.
Now
when I grew up, how old I am, magnetic pole was in the northern territories of Canada.
Wow.
But it's been shifting.
It's been shifting, right?
Yeah, because North Pole is a wandering thing.
Yeah.
And right now it's passing the North Geographic Pole.
Okay.
It's just closer to that than it's ever been before, and it's headed towards Siberia.
There you go. So it's actually where it belongs, where we say it is.
Right now,
is the North Pole, the Santa Claus Pole.
It's near the North Pole.
It's near the North Pole.
And Putin is going to have control over the North Pole. What do you got next?
All right, here we go. This is Mile Milkovsky. Okay, Mile says this. Hey, Neil. Hey, Chuck. My name is Mile. I'm from Macedonia, Balkan, Europe, world.
I like that.
Yeah,
okay.
that's very cool. He says, we see a lot of matter goes into energy in the universe, but do we see the other way around, energy becoming matter?
Yes.
Oh,
yeah. Well, yeah.
Okay.
Yeah.
Okay.
So in the sun, in the center of the sun, there's thermonuclear fusion. Hydrogen nuclei merge.
Right.
Okay. So here's what happens. Ready? A hydrogen only has one particle in its nucleus.
Right.
A proton. So there's just protons there. So one proton meets another proton.
Hey, how you doing?
Okay.
What's up?
Hey, there you go. How you doing?
Right.
Okay.
How you doing?
Protons have like charge.
Right.
So like charges do what?
They don't like each other.
They repel.
That's right.
So in order for them to get close together, they have to be moving so fast that their speed overcomes their repulsion. And they're so close to each other that a whole new force that's strong has to kick in. And you know what we call that? We call it the strong force.
The strong force.
Yes,
Right.
it's sensibly titled, the strong force. In that moment, one of those protons becomes a neutron.
Oh.
It transmutes. So you have a proton and a neutron. Wait a minute, we started with a positive charge.
Right.
Now there's a neutral charge. What happened to the positive charge? You can't just pocket that.
Right.
Okay? A particle comes out carrying away that charge.
Okay.
It's the antimatter version of an electron.
Whoa.
It's called a positron.
A positron.
Okay? Now, this is a soup of ionized atoms. Right. And when you're ionized, electrons are flying everywhere. If you're a positron and you're antimatter positron,
right?
If you see an electron, that's all she wrote. You annihilate
Look at that.
instantly,
Instantly.
creating energy in the
Look at
center of the sun.
Look at that.
That's one of many ways the sun is generating energy in the core.
Wow.
That happens every moment of every day. 2 particles of matter coming together and creating pure energy.
Look at
The
that.
positron and the electron in the core of the sun.
That is amazing.
So yeah, but it doesn't happen around the house.
No, no.
But it would.
If you had a sun.
A sun, S-U-N.
Right.
Yes. So now watch. Here's the thing. Light that we use, visible light.
Visible light.
If you look up how much energy a red light photon has or a blue light photon, just look up how much energy that is. There is no particle that can be made with that much energy because it's not enough.
Okay.
So light, visible light stays visible light its whole life.
Wow.
Increase the energy up to beyond ultraviolet
Ooh.
into X-rays.
X-rays.
Oh, now ask yourself, what is the energy of an X-ray photon?
Mm-hmm.
It's about the energy of an electron.
Ooh.
So you can have a field of X-ray photons with electrons spontaneously being created within it.
Oh.
Okay?
Okay.
Now, but you can't just create a particle out of nothing. You also have to have the antiparticle.
Right. Okay.
So if you create electrons, you're also creating what?
The positron.
Positron.
Right.
There you go. And so that's energy
And
becoming
being
matter.
Matter.
Right.
Look at that.
That's the inverse of that he was asking me about.
Yeah, exactly.
And then they find each other again and they become matter. This soup was going on in the early universe in every cubic centimeter of the universe.
Look at that.
Matter going back and forth
Just-
until the universe cooled,
Right.
where none of the photons left had enough energy to make particles.
Oh, Lord, I'm so tired.
And we froze out the total number of particles in the universe in that moment.
Look at that.
No longer could you make more particles.
That's it.
That's it.
All right, let's go with Andrew Coffey.
Mm-hmm.
And Andrew Coffey says, "Good day, Dr. Tyson and Lord Nice. Wishing you a wonderful wisdom from a few fine fellows. Andy C. here from Vancouver, British Columbia.
All right.
I've always
That
wondered.
would be Canada.
That's
Yes.
right.
Mhm.
I've always wondered, how did we first calculate the speed of light in a vacuum? And how do we know it's a constant? Is it possible we could be wrong?"
Oh. Speed of light in a vacuum.
Yes.
Okay. Galileo is the first one known to try to measure the speed of light.
Look at that.
At night, he put somebody on a mountaintop with a lantern and a
Right.
little shutter.
Right.
Okay, and he was on another mountaintop with a lantern and a shutter. And
Right.
and they said, when you see one,
Give it back to me.
give me the signal back with the shutter. And he concluded, light, if it's not infinitely fast, it's faster than we could measure. Okay.
Nice job, Galileo.
Just tell it like
a nice
it is.
job, right.
That's all you know.
Yeah, that's it. That's what we know right
Can't tell more than what you can know.
now. There you go.
Okay. So, do you know the distance from Earth to the center of the sun? I mean, to the sun?
93 million.
Okay, so twice that is
186
million
miles.
miles. Okay? Keep that number in your head.
Okay.
Okay? That's the baseline of Earth's orbit
Okay.
around the sun.
All right.
Okay. A guy named Ole Romer,
Okay.
Ole Romer, it's got one of those umlauts
Right,
with the
yes,
O-E,
yeah.
okay?
Ole-
Ole Romer,
Okay.
at the time he did this, we knew that the Newtonian gravity
Right.
not only described the moon around Earth, Earth around the sun, it described Jupiter's moons around Jupiter.
Okay.
So you didn't have to be the sun to be the center of gravity for a system. It worked for Jupiter too. So this was a testament to the universality of Newton's laws. Because if it just works for the Earth and Moon, maybe it's just Earth Moon.
Right.
You don't know that it works everywhere else. It works everywhere else.
Okay.
All right. So you calculate when the moons pass in front of and behind Jupiter.
Okay.
What he found was that when Earth was closest to Jupiter, the eclipses occurred 1,000 seconds sooner than when Earth was on the opposite side of the sun from Jupiter.
Okay.
He said either Newton's laws are wrong, or we had to wait for the light to cross the entire orbit of the Earth to get to you. Because on the backside of Earth, it was 1,000-second delayed compared to the front of your orbit.
Right.
So, what's the formula for speed?
This
Distance divided by
time.
time. What's the distance?
186 million miles.
What's the time?
1,000 seconds.
What is the speed of light? Take those two numbers, you divide them. 186,000 miles per second. Now, we didn't have the diameter of the Earth. The guy had the wrong number for that. It was the most accurate estimate of the speed of light yet to be made. Just the delay in the eclipses of Jupiter's orbits.
Right.
Depending on where you are in our orbit when you're taking a look at them. And the numbers turn out all nice and even, right? 186 million miles,
right.
1,000 seconds, everything was clean and easy.
Right.
Okay. Now we're sophisticated. We can measure it in a laboratory. We can do what Galileo attempted to do. Sure enough, we get the same number.
Look at that.
Okay? Every time we've ever measured the speed of light, we get exactly the same number. At all times.
At all times.
Correct. And we look at other parts of the universe where we see phenomenon happening. Speed of light's the same. Right on up to the edge of the universe.
Cool.
So our evidence, and since as you look out in the universe, you look back in time, we can say with confidence that the speed of light is the same and unchanging across space and through the depths of time. It is the most fundamental constant of nature we know.
Yes. Yeah.
It is so fundamental that we define the length of the meter in terms of the speed of light.
Wow. Okay.
So if we make an extra measurement of a decimal place in the speed of light,
Okay.
that affects the length of the meter. That's how badass the speed of light is.
Right.
It's running the show.
Look at that.
So a meter is how far a beam of light goes in 1/30 millionth of a second. Yeah, it's the right 12 decimal places.
Wow.
Yeah.
That is super cool.
Now, the speed of light is different in the air and in water and in a diamond, but in the vacuum, that's the speed.
Right, that's the speed.
Yeah.
Right.
And 186,282 miles per second.
Wow.
Or 3 times 10 to the 8th meters per second. But it's really it's like 29,990,000. We round that up. It's a nice rounding to 3 times 10 to the 8th. So that would be 300,000 kilometers per second.
Okay.
And now you make meters and centimeters out of that.
Out of that.
Right. And so, but it's really like 299,000 something. It's close, but we round it up to 300,000 kilometers a second. 186,282 miles per second.
Cicero Artefan from Toronto, Canada here. How do we entangle particles? It's mentioned that when we measure one particle, we instantly know the measurement of another. But how exactly do we entangle them? Is it a matter of taking two particles, entangling them, placing one in a box, shipping them to a different city, and then conducting the measurement? How do we know they are entangled?
Oh, because they are born together.
Ooh, look at that.
Ooh. Ooh, so there's a state of existence.
Right.
Of a pocket of energy or matter. And if you create two particles out of that state,
right,
the two particles have complementary properties,
okay,
which when combined equal the properties of the conjoined state.
Right.
When you separate them, they take properties of that state with them. Okay, and then they go apart.
Right.
And then they are quantum mechanically entangled.
Gotcha.
Thenceforth. But they're born together. You can't.
Right. You can't. You don't go recruit
particles.
Yeah. So born together. That's
born
the
together.
deal.
And the tricky part is if you meddle with one of the particles in the slightest way,
right,
then it just you collapse what's called collapsing the wave function. They're entangled because their waves overlap,
right,
and they have a common knowledge of each other,
right.
And if you make any measurement at all, the way we say it, without declaring that we truly know what the hell is going on here,
right,
the wave function collapses and it becomes the discrete individual particles, and they're no longer entangled.
That's really cool.
Right.
That's amazing.
Right, and that entanglement, they communicate with each other instantly.
It's instantly.
Yeah, it's
right.
not even about the speed of
light. Yeah,
light.
not even the speed of light, just instantly.
Instantly.
Yeah.
It's mysterious.
Yeah. But still not a way to send information, which is...
No, you can't. No.
Why wouldn't you be able to send information?
If there's a way to do it, no one's figured it out yet.
Okay,
but
and that's the way you should say it,
Yeah,
right?
yeah, yeah. I'm a scientist, that's the
right,
right way to say it.
that's the right way to say it.
right now, so we want to send information. Am I sending information in a locked box and then the box opens when you get it?
Right.
In a way. But when you send information, it's because you learn something and you want to alert your troops or alert your friend.
Right.
At that point, you're not opening a portal through the space-time continuum to send the information.
Right.
You're not doing that
Gotcha.
at that point. So we're still thinking it through.
All right, cool.
By the way, we have a quantum entanglement gap between the United States and China. They've been quantum entangling more than we have, and they have the distance record for it.
Oh, I understand.
Like from orbit to Earth's surface,
right,
this sort of thing.
Right.
They found a way to isolate the particles so that they don't get messed with.
Okay,
Yeah.
and then
So if it matters in the future, who has the biggest quantum entangled distance?
Mhm.
We're going to lose that. We're going to lose it.
get with it, America. Now you know.
That is.
Listen, can't let somebody out entangle you. That's the deal. All right, Ernesto Medina. He says, "Is it true that you get more wet when running in the rain than if you walk?"
Yeah. So that's a fun question.
Yeah.
And I've thought about that my entire life. It's an interesting question because if you go slowly,
Right.
okay, then the rain just accumulates.
Right.
If you run fast and you're running into raindrops.
Exactly.
Okay. So while I did not arrive at a definitive answer, I arrived at an answer.
Okay.
Okay.
All right.
It depends how fat your head is and what your cross-section frontal body is.
Right.
Okay? Because if you walk in the rain, the only part of you that's getting wet is the part that's falling directly on top of you. So your shoulders and the top of your head.
Hence the umbrella.
And so you get you want to, if you have an umbrella, you want to send it away from you.
it.
Okay.
Right.
So you get that area.
Right.
And you look at the raindrops per minute that's hitting that area and how fast you're walking across the street. You can calculate that and get a total number of raindrops that you hit if you go slowly. If you go slowly enough, you're not going to hit rain in front of you. Right. It's all just going to come to you.
Right. Exactly.
Now, if you run, rain is still going to hit you on your head and shoulders, but for not as long.
Right.
But now you have your entire surface area of the front of your body that's running into falling raindrops.
Right.
So you have to calculate those two. And because the rain, let's assume, is all falling at approximately the same rate because it's gravity and air resistance and the right. So it's really a matter of how far you're going, how fast are you going,
Right.
how fat is your head, and what is your frontal cross-sectional area. And those two operate against each other in the equations. And so you solve the simultaneous equations, and then you get, it's called in calculus, a minimization problem.
Okay.
Okay? And you use the tools of calculus to either minimize or maximize something.
Okay.
And typically you have two equations that are operating in opposite ways.
Right.
And it's the middle
where
of
they
those two,
intersect.
where they intersect.
That's
It's not much different from in economics,
Right.
where you have the
supply and demand,
and they're both
curves
going in different
come
directions
together. Right.
because the higher the price, the lower the demand.
Exactly.
And there's a point where the right price and the right demand maximizes.
And that's your point of equilibrium. Yeah.
Yeah.
That's
no, your point of maximum
profit. Right. Right. So that's
maximum revenue, I should say. Your profit.
Right. Your profit
is
is dependent on everything. Other
how much
factors.
you pay your elves.
Right. Exactly. Which is nothing.
Nothing.
That's right. All right. Here we go. This is Adam Weiler. He says, "You say that on Earth we don't experience physics like the rest of the universe."
I've never said that, but go on. I have an entire essay titled "On Earth as It Is in the Heavens."
Oh, okay.
In fact, it's a chapter in my Death by Black Hole book.
Okay.
So I don't know what this man is saying.
Well,
but we'll hear him out anyway.
No, listen. That was it. He said he was upset.
On Earth as it is in the heavens.
He says, "You say that on Earth we don't experience physics like the rest of the universe. Why would things be different?" That's what he says.
Okay,
this is Adam Weiler.
I will offer Adam an answer, even though he didn't pay any attention to anything I said or wrote. Okay,
Exactly. What do we got?
I have in my hand
Death by Black Hole.
Death by Black Hole.
All right.
And all I'm going to do is read the first paragraph of that chapter. Okay, it's chapter freaking 2 of this book.
Okay.
Okay, On Earth as It Is in the Heavens. Until Isaac Newton wrote down the universal law of gravitation, there was little reason to presume that the laws of physics on Earth were the same as everywhere else in the universe. Earth had earthly things going on, and the heavens had heavenly things going on. Indeed, according to many scholars of the day, the heavens were unknowable to our feeble mortal minds. The universality of physical laws drives scientific discovery like nothing else. And gravity was just the beginning. Imagine the excitement among 19th century astronomers when laboratory prisms, which break light beams into a spectrum of colors, were first turned to the sun. Spectra were not only beautiful, but also contained oodles of information about the light-emitting object, including its temperature and composition. Chemical elements reveal themselves by their unique patterns of light and dark bands that cut across the spectrum. To people's delight and astonishment, the chemical signatures on the sun were identical to those in the laboratory and to those in stars across the galaxy.
In other words, it's the same no matter where you are.
Not only in space, but in time.
But in time.
Yes. So now that he's been chided, let me offer him a comment.
Okay.
A reflection on the, okay? We experience macroscopic laws of physics.
Okay.
Newton's law of gravity,
Right.
Electricity, this macroscopic laws of physics. If we were really, really tiny, the world would look different to us.
Yes.
Because then we'd be experiencing the world of atoms and molecules.
Right.
And quantum physics
Right.
rules in that regime.
Right.
Whereas macroscopically, quantum physics manifests as classical physics.
Gotcha.
Quantum physics is everywhere,
Right.
but the detailed behavior manifests more readily on the small particles than a big particle. So, we thought, oh my gosh, the atom has electrons that orbit it, just like the sun has planets that orbit it. Maybe it's orbiting things all the way down.
Right.
Just a whole other little universe.
Right.
No, it's not. In fact, it still holds the word orbit, but we made a new word and call it orbital.
Right.
Okay, so electrons move in orbitals around the nucleus. But the orbit in that phrase comes from classical physics. So things are different when you're small, but when you're our size, no, same macroscopic
Same
physics.
deal, no matter where you are.
Correct.
There you go.
All right.
Actually, Adam, thank you so much for that question because that was really cool. That was good stuff.
Okay.
Yeah.
But it meant he actually
he was incorrect in his assertions, but still, it was good.
It's an important thought that needs to be addressed.
Exactly. This is Troy. He says, hello,
Troy
Neil. Just Troy from Virginia.
Troy.
He says, hello, Neil. Hey, Chuck. Troy from Virginia here. Can objects exchange dimensions with one another in a way that would be similar to thermodynamics or entropy? Ooh. Damn. Somebody was smoking some good weed, boy. Let me tell you.
So I don't think we command dimensions.
Yeah, right.
We are prisoners within them.
Yeah.
Take time, for example. We are a prisoner of the present.
Right.
Forever transitioning between our inaccessible past and our unknowable future.
Right.
We don't wield this dimension, we live it. So if one day we discover that we could detach a dimension from us,
right,
that would be an interesting world.
Amazing.
If you could give up like your depth instead, but keep your height and width.
Are you kidding me? I'd be slipping under every door
yes,
there
you
is.
could, and slip between the doorways.
That's right.
But so it's a fascinating thought.
Yeah.
But I'm resistant to how real that could be.
Right.
Because everything we know about the dimensions keeps us prisoner within them.
Now, could it be that something like dark energy could be the pressure that we're experiencing from another dimension, since dark matter doesn't interact with anything that we know of?
I could say anything I wanted about dark matter and dark energy.
Right.
And
it wouldn't make one
we
bit
don't-
of...
They're both completely mysterious entities. They're so mysterious that people have the urge to explain other mysterious things with them.
Right.
Well, we don't understand consciousness, must be dark energy.
You know what it is? It's the collective consciousness of everything that's ever been in the universe.
That's the dark energy.
That's the dark energy.
Right. So it's fun headlines and good beer talk, but it's not good science to take something that you don't know and explain it with something that you know even less about.
That's such a great point.
It's just as simple.
And that is why I am not a scientist, because
you explain stuff all the time.
Because that is no fun.
Because people I don't mind mysteries, but like
Right.
one at a time.
Yeah.
You want to stockpile mysteries and have them all be the same? No, I can't do that.
Okay. All right. Well, damn, that's great. All right. Thank you, Troy. That was a great question. All right. Here we go. This is Thomas Asserd. Hello, Dr. Tyson and Lord Nice. I am Thomas. I'm 24 years old, and I'm writing from southeast Norway. My question is, could we, in theory, of course, send a satellite into orbit, a black hole at a safe distance, launch a probe from said satellite, and use quantum entangled particles in the satellite to probe to get any kind of data when the probe enters the event horizon, or would it all turn to spaghetti and just be unuseful?
Wow. Man, what kind of fan base we have?
Listen. Listen, if we had the money, that's the way to do it, though. I mean, in terms of the probe, you know.
I'm just talking about how our people are thinking.
They're thinking.
What kind
That's
of brain
good stuff.
wiring is in our people?
This is good.
This is our people. Okay, so why does the probe have to orbit the Earth if it's going to visit a black
it's
hole?
orbiting the black hole.
Oh, it's orbiting the black hole. I missed that.
So we send the probe to the black hole.
Got it.
It's orbiting the black hole.
Got it.
But not at a distance where it can,
be sucked in.
Right.
Yeah,
It doesn't enter the gravitational pull of the
There
black
are distances where there are no stable orbits, so you just stay outside of that.
Right.
Okay. So
then now what we do is we send a probe into the black hole,
Yes.
much like a probe going into a tornado,
Okay.
and we take as much information as it approaches the black hole
Yes.
until we can't get any information anymore. Now, here's his next question. Could we then use...
that would be cool. I would do that.
Okay.
I would totally do that.
We would totally
Yes,
do that.
yes.
All right, that's great. Now, the next part of the question was, and I think you already answered it earlier in the show, could we then use quantum entangled particles so that once we're in or past the event horizon where no information would be able to escape,
Other than by Hawking radiation. Yes.
What we would then do is use the quantum entangled particles to receive information about what's inside the black hole the same way as they evaporate.
Okay.
One particle appears on the outside, the other one goes back in. So
Okay.
boom.
Okay. All that's happening is your particles are coming back out.
Right.
That's it.
That's it.
Yeah, so it's an interesting idea. We'd love to have an orbital thing just to get close-up data. You got to watch out, though, because if it gets too deep in there, we saw this correctly done in Interstellar, where if you get too close, your time frame gets so different.
Right.
So different. So I live a year, and you get 10 minutes of data you sent me.
Exactly.
Because for you, it's a long time.
Right.
But for me, up in the orbit, I'm not getting the data rate that would be useful to me.
Right. Okay.
So you can ask, isn't this a good use of telescopes? Why do I have to get all up on the black hole? Let me go a distance away and get a really big telescope and get all the data.
And just get as much data as you want.
Yeah.
Right. Okay. There you go.
Mhm.
All right. Here we go. This is our old friend, Alejandro Reynoso. What is your favorite discovery or invention that happened in your particular lifetime?
All right. So in my lifetime,
Right.
there's some discoveries that just slowly accumulate
Right.
and don't represent the work of a lone scientist burning the midnight oil. And these other categories of discoveries never make headlines because they just sort of leaked into our awareness and understanding from the body of work of dozens and sometimes hundreds of scientists. In my lifetime,
Okay.
this is how old I am, we learned
Right.
that, and though we haven't checked every galaxy, everyone we've ever checked has a supermassive black hole in its center.
Okay.
Enough so that we're going to say every big galaxy has a supermassive. That's a discovery in my lifetime. A. B. In my professional lifetime. Right? This stuff when I was like 5. I don't care about that. Okay.
Right.
All right.
Okay.
But I was born after the discovery that the heavy elements that populate the universe and including life on Earth, including us, derive from stars that manufactured them in the crucibles that are their cores, and then exploded, scatter that enrichment across the galaxy to enable nascent star systems to have the right ingredients to make planets, and on some planets make...
I don't know. People.
Yeah, people. Just spitballing here.
Yeah.
People.
Yeah.
So I've existed in this world only in the era where we've known the origin of the chemical elements.
Look at that.
Okay, let's keep going. So discovered black holes, supermassive black holes in the centers of galaxies.
Right.
We've also tightened our understanding of the age of the universe. When I was in graduate school, the uncertainty to that number was a factor of 2.
Mm-hmm.
There was a camp that said, oh, the universe is 10 billion years old. Other camp says 20 billion years old. And that's a factor of 2. That's embarrassing. Really.
That's terrible.
If you don't know how old you are to a factor of 2, go
yeah,
home.
that's bad news.
That's bad. Go home.
Yeah.
But we knew a factor of 2 is better than a factor of 100.
That's true.
Okay. And so for many of us, we were fine. We were in the right ballpark.
Okay.
So over time, that has narrowed to, it's not 10 billion years, it's not 20 billion, it's 13.8. Okay.
Right.
And there's some uncertainty there still.
Of course.
But it's not a factor of 2 uncertainty.
Yeah.
So questions that were of paramount significance and meaning in my lifetime have become just simple knowledge that everyone carries, and we're asking other questions about the universe.
Cool.
So if you had asked me in the 1980s, what's the most pressing question? It was the value of the Hubble constant and the age of the universe. And now nobody's asking that question. Not in the way we were asking it back then.
Mm-hmm.
So I would put those very high up.
That's
on
great.
that list.
Okay.
Mm-hmm.
That's very cool.
Yeah.
That's very cool. Let's go to, this is Isaac Huerta. And Isaac says, hey, Neil, I appreciate everything you do. You continue to inspire and motivate me to educate myself and others. I was wondering, with black holes having an infinite density, what happens to the particle's activity living inside of it and their particle lifespans? So
No, I can answer that. We have no freaking idea.
yeah.
In fact, so let me say it scientifically accurately. You ready?
Go ahead.
All our knowledge of matter, motion, energy, and physics tells us that when mass collapses on itself,
Right.
so that it collapses smaller than what would become its own event horizon,
Okay.
thereby turning into a black hole, there is no known force to prevent the collapse to infinite density in 0 volume.
Jesus.
Einstein said there's got to be something to prevent that.
Of course.
Something's got to save us from ourselves
Right.
in this. We don't know what that is. We got top people working on it. These are the string theorists.
Right.
The top people who think about the singularity, that's called the singularity,
Exactly.
who think about it at the center. And maybe there's a loophole. Is it just a mathematical singularity rather than a real physical singularity?
Mm-hmm.
So the jury's still out on that. But we got top people working on it.
Okay.
Yeah.
All right. Great
Because
question.
how can anything have 0 volume and infinite density?
How could,
I mean, they're related, of course.
right.
You know.
But still.
Yeah. Yeah, but there was a day you could say, how could the universe have had a beginning? It clearly always was. Right. There's a lot of how could something have happened? And then sure enough, that's what it is.
Yeah. Yeah, exactly.
Yeah.
How can particles pop into
existence, right?
How can that even happen?
Yeah,
that can't happen?
Yeah, right.
Just can't have things pop out of nothing?
Yep.
Oh.
Right. So for me, I never say that anything can't ever happen.
Right.
I'll just say we have not yet discovered whether it can.
Okay.
Yeah.
So this is Fabio Latter.
No, Fabio.
That's it. Fabio. He says, greetings, Dr. Tyson, hailing from, whatever. The paradigm of time has always fascinated me, especially in regards to how it will shift or evolve after humanity explores the solar system and beyond. How do you think our understanding of time will change on different planets when drifting between stars thanks to time? So I think what he's saying is when we, and how very optimistic of him, when we seed the cosmos with our presence.
With ourselves.
And we know that time is different in different places. What will our concept of time be when we're all trying to be in contact with one another in these disparate places?
Okay, I think you added stuff to his question.
Well,
but all right, okay, but that's fine.
that's what he's saying.
Okay. So there is the flow of time, which changes depending on how fast you're moving and how strong is the gravity field you're in.
Right.
Okay, we are orbiting the sun in an Earth gravity field. Our time ticks at a particular rate. GPS satellites orbit high up.
Right.
They're in a lower gravity field.
Right.
Their time ticks at a different rate from ours.
Right.
So when it sends us the time, we have to correct it for Einstein's general theory of relativity.
Okay.
Okay. But people don't know that. We're just pulling time out of the sky.
Super cool, man.
It's too. Einstein was a badass.
Yeah, he was.
Is what that is.
Because it's real time and it's not moving at the same rate.
It's not the same rate.
All there
And
is to it.
it's no less authentic.
Yeah, and it's no less. It's the actual time.
Actual time.
in both places.
In both places.
Gosh,
Correct.
So crazy.
It's crazy. Okay. So now you have descended into a gravitational well where to escape, you have to climb back out of it using energy to do so.
Okay.
That's why we think of it as a well. So if we have people living on different mass planets in different gravitational environments, traveling at different speeds around their host planet,
Right.
the measurement of time will be different for all of us.
All of them. Right.
Okay? So you'd have to be careful if you were planning an event that was supposed to happen simultaneously for any one particular viewer. And there's no such thing as simultaneity because things can happen all at the same time for you, happen in a different order for someone else,
Right.
depending on their speed relative to you. So synchronization will become something much less useful.
Right.
I don't know how else to say it.
Yeah. Yeah. It just won't be an order that people want to consider because it's not happening.
It's not happening.
It's not happening.
It's not happening.
Right.
You can't do things together if you're separated by light years in time.
Yeah, exactly.
Right.
All right.
Okay.
There you go. It's a cool. I know why he says that. Though,
And have a weird off-ramp to this.
Go ahead.
Okay. There's a limit to how big a life form can be because if it has an itch and it wants to scratch it, if they're really, really, really big, let's say the size of our galaxy, it'll take them like 100,000 years just to scratch it. So there's certain physical limits to how much witty repartee you're going to have with somebody in another place.
Right.
Across the galaxy. All right.
There you go. There's another question, and I normally don't repeat questions.
What?
But
I mean, from the same person?
yes.
Really?
And guess who it is?
Who's that from?
Cicero. He says, "Hello, Dr. Tyson. If I were to construct a wormhole, how cautious would I need to be? What could happen if we were to open it in the wrong location? If the other end leads to the vacuum of space, or if it's close to a black hole? Would everything be drawn into the black hole from my wormhole? Could the vacuum of space pull everything surrounding the other side of the wormhole?"
Through the wormhole.
Through the wormhole.
Yeah.
If you open a wormhole and you could place it, would you have to be careful? If you can place the wormhole anywhere, that's the whole point.
I think if you can go through the wormhole, so can other matter, and so could energy and anything else while the portal is open.
Right.
I don't see anything preventing things from. You could even be pulled through the wormhole. If there's a strong gravity. So yeah, you got to know what the other end of the wormhole,
where the other end of the wormhole is.
You got to know in advance
Right.
where you're stepping.
Don't want to end up in the toilet of the galaxy,
Yes.
which is that black hole in the middle.
If you can go through, so can other things. So be careful where your wormhole opens first. Second, we currently know of no way to, in a sustained form, keep a wormhole open, preventing it from collapsing.
Right.
Because we need a negative gravity substance to pull the fabric of space-time apart.
Right.
And everything we know that substance does is pull it together with the force of gravity.
Right.
So this has to be, we need a negative substance. And that might sound like, that's crazy talk,
Right.
right? Negative substance gravity. But how different is that from the people who stood flat-footed on Earth, looked up and said, I want to go to the moon.
Right.
And if a future person says, well, you need rocket fuel, what's that?
Exactly.
Well, it's this mythical substance that can launch you from Earth into space to the moon. People look at you like you're crazy.
That's right. Yep. This is Christine Tolman. She says, "Hi, Neil. I'm from Phoenix, Arizona. I'm a teacher. What are some good books about the nature of the universe for very young readers?" Okay.
There's a book called Look Up With Me,
Right.
which is for you just barely learning how to read.
Mm-hmm.
And that's a bio kids book about me. I didn't write it though, but I think I wrote the foreword to it.
Okay.
With a preface or something. And it's got pictures and it shows me learning how to become a scientist at age 9. So it's very early on, but it's a picture book, which by the way was briefly banned in Pennsylvania.
Okay.
In your freaking home state.
Well.
Because in there, they tell the story of when I was on the roof using my telescope I was 13 years old, 14, and then the cops come because someone else called the cops because they see this bazooka-looking thing sticking over the roof of my apartment building.
Right.
And they said, must up to be no good.
Right.
And then they come. And I showed them Saturn, and that usually wins them over.
Wow.
You got to do that before they pull their gun and pull the trigger.
I was going to say.
And then of my best-selling book, the Astrophysics for People in a Hurry, there's a version of that written for tweens.
Okay.
Age 7 to 12.
Awesome.
And that's called Astrophysics for Young People in a Hurry.
There you go.
There it is.
All right.
Both of those. And that's co-written with Gregory Mohn. He's really good in transitioning from an adult book to a kid's book. So there it is.
This is Will Holland. He says, "Hey there. Will from Kentucky here. What's the coolest thing from sci-fi movies or books that you think will actually become a reality in the future? Thank you.
Ooh.
Yeah.
Ooh.
Yeah.
I think the entire movie, The Matrix. How do you know you're not just
Living
imagining
in
all
us.
of this?
Right.
How do you even know that? You don't.
You don't.
So I kind of like the themes covered in The Matrix.
Nice.
The distinction between your brain's reality and an objective reality and who's in control. Those were fun.
And we're moving towards that.
Yeah.
Okay.
And in Star Trek, I think we will have wormholes before we'll have transporters. Because think about it. Wormholes will render transporters obsolete.
Yeah, you don't need them.
I don't have to particle beam you and send you somewhere. Just step through like Rick and Morty.
That's a recurring theme in the Star Trek series, that they're always in search of a stable wormhole.
Oh,
Yeah.
so they know.
Yeah.
And if they do, then if you can master them, then it's a wormhole transporter.
Right.
You just step through. Like our dude who from the Marvel, Doctor Strange.
Right.
And I've said this before, I got to say it again. Okay? Doctor Strange can open a portal, which is basically a wormhole, to another place. So too can Rick and Morty, or Rick specifically.
Rick, right.
Okay? The difference is
Yes.
Doctor Strange uses magic and Rick uses actual science.
Yes. Jarrett Rice, he says, hello, Brainiacs. Yeah, Chuck, that includes you too.
Oh, is that a compliment or insult?
I don't know.
Okay.
I'm going to, wow, Jarrett, I'm going to take it as a compliment.
Okay, good.
This is Jarrett from Fontina, California. I've always wondered, can rocky inner planets have rings like Saturn? And would those rings impact the tide bulges?
Oh.
What a nice question. Way to go there, Jarrett. I like it.
Ooh.
So,
okay.
not a gas giant.
Okay, so all 4 gas giants have rings.
Yep.
Only one of them is it particularly spectacular, and that is Saturn.
Right.
Calculations that I've seen recently suggest that in the time of the dinosaurs, Saturn might not have had any rings at all.
Look at that.
Or the ring that we see would not have been visible.
Right.
And that the dynamics of ring systems might be finite, lasting thousands or millions or tens of millions of years, but not a forever thing.
Okay.
Okay. We certainly had a ring when the moon formed.
Right. Earth had a ring.
Yes, we certainly had a ring
Right.
when the moon formed. But what do you think happened to all the particles?
They got sucked up. Well, wait. They became the moon.
They became the moon.
They became the moon.
Okay.
Yeah.
Yes. Okay. If you have something there ready to grab whatever is moving by,
Right.
okay, they're all going to see the gravity of this new. And if you have slightly more, think of how the moon formed. It's a big ring of particles, of rocks, okay, from the collision of Theia with Earth in the early solar system. And if there's a slightly bigger rock than others, it has slightly more gravity than everybody else. So it'll get a few extra particles than you are. Now it has even more gravity
Right.
to get even more particles.
Right.
It's a runaway process. You heard the joke, there's no such thing as gravity, Earth sucks, right? You heard that. Okay. So in orbit, the moon would have sucked up all the particles.
Exactly.
Okay. So now if you look at Saturn, Saturn's ring has gaps in it.
Yes.
Gaps.
Yes.
When we had a good enough resolution to see inside the gaps, there's satellites that cleared out those gaps.
Ah.
Yeah.
Look at that.
Tiny satellites.
Yeah,
but
they're
they
like
cleared it
little
out.
moons.
Well, yeah, that's what I meant. Moons that vacuumed up just their
Just
what's
their
in their
little
radius.
part of the
little
ring.
part of the ring. Exactly. So we have a big moon relative to our size,
Right.
and that would have just taken the ring out. So you're not going. I don't think you're going to get a fully sustained ring.
All right, let's jump into it with Danny K. Because in a previous episode, there was a mention of an expanding of our universe and that there could be a point in the distant future where we would be stretched to a point where our neighboring galaxies would be too far to reach. Would this expansion also affect our solar system as well? Does it mean that our blue ball would slowly drift away from our star? And would our star dim before that time comes? And if so, would you suggest how we might be able to survive something like this?
Yeah, so in the vacuum of space, there's this mysterious pressure forcing an acceleration of the expanding universe. We have a word for it, but we don't know what it is. We had no business naming it, really. And it's called dark energy. And I joke that we should just, dark matter, we don't know what that is either. We should just call it Fred and Wilma, just 2 words that don't hint at anything physical, right? Because we don't really know what's causing it, but we can measure it. And so this expansion of the universe that's accelerating, that will continue to grow. And the bigger the universe is, the more vacuum there is, and this pressure is a property of the vacuum. So, as the universe expands, the gravity gets thinner, what we call the gravity density gets thinner, but the dark energy continues to grow relative to the gravity. So initially, all the galaxies will expand beyond our horizon. And then after that, it will start ripping apart the galaxies themselves.
Ooh.
Because that's a stronger gravitational force holding them together. Start ripping that apart. And so the solar systems will be flung hither and yon. Then it'll start ripping the planets out of their solar systems. Then it'll start ripping moons from their host planets. Then it'll start ripping planets apart structurally. Then it'll start ripping apart the molecules. Then it'll start ripping apart the atoms in the molecules. Then it'll rip apart the nuclei of the atoms. Then it'll reach the point where the very pixels that comprise the fabric of the universe will succumb to this ripping force. And it's called the Big Rip because we do not know what will happen after that moment. At that moment, the universe will tear because it will no longer be able to stretch in response to that force. We call it the Big Rip, and it will happen if nothing else is in the way. It's going to happen in 22 billion years. So yeah, the sun will be long dead by then. Sun will give up the ghost in about 5 billion years. We're about halfway through the life expectancy of the sun. But the sun will be dead long before that happens. And so I wouldn't worry about it.
All right, this is James Booth, and he says, my question is about dark gravity.
Okay.
I understand it.
Which is what most people would call dark matter. But he knows I'm calling it dark gravity because that's literally what it is. It is gravity, and we have no idea what's causing it. It's not even black holes, by the way, or unilluminated matter. We have good reason to know that that's the case. But go on.
He says most of the matter we experience that makes up the stars of galaxy only makes up about 5% of the content of the universe. If that's the case, which you just said it is it possible that, given we interact with such a small percentage of the universe, we are indeed the anomaly? This really makes me feel weird.
It's imagine you're at night and there's an ocean in front of you, but you don't really know it. And you turn on your light and you see these white caps, okay, which show up nicely under moonlight. And we are the white caps of an ocean that surrounds us. So, correct. We are, if there were beings made of dark matter, dark energy, they would see us as a contaminant in their universe.
Oh,
that's
look
right.
At that.
Yeah, I know.
Wow.
It's sad.
Well, yeah, it is. I mean, but
You're
it makes
not
sense.
representative of the most common stuff in the universe, which, by the way, is a violation of the Copernican principle. Copernican principle says that we are not special in time or in place or in location. We're orbiting an average star in an average galaxy. So statistically, it says that we're average. But if we are contained within that 5% of all the laws of physics, chemistry, biology, and all the ingredients that make up matter as we know it, then we are something unusual in the universe.
But could we be the average inside of the unusual?
Yes, we are. Yeah. So I was going to complete the thought and say, given that we are unusual, we are average.
Very nice, very nice.
Another example of that is, you know how school systems try to corral all the smart people together, right? Well, they used to do this. They put the smart people in their own class. Okay.
All the AP kids are in.
Exactly. So in the general population, you're unusual because you're like smarter than everybody else. Then they put you in the AP class, and now you are
just average.
You're just average. You see,
everybody's
that's
smart. That's right. This is, let's go to Rotten Josh, aka Transmetal 2. Hey guys, this is Rotten Josh here from Somerville, Florida. My question, instead of the Big Bang, could the universe have formed from a big implosion instead of an outwards explosion? When I think of the Big Bang, I imagine exploding outwards. So I was thinking maybe it exploded inwards. And thank you for your time.
Before we had good data on the very distant future history of the universe,
Right?
there was our equations that are traceable to Einstein and others, including what's that dude's name? He was a Belgian priest, actually, who contributed mightily to our understanding of the Big Bang. And he, so but anyhow, so it, under the Einstein's equations, it can sustain a collapsing universe as well as an expanding universe. So people naturally said, if we measure an expanding universe, maybe it'll one day recollapse and then start all over
Start
again.
all over.
Yeah,
Okay.
and that's where you get this sort of these rhythms. By the way, the name of that Belgian priest is Georges Lemaitre. Georges Lemaitre.
Georges
Yeah.
Lemaitre.
Lemaitre, yeah,
Yeah.
yeah. And so he took Einstein's equations and said, wait a minute, this can give us an expanding universe. And if we're expanding, that means it had a beginning. If it had a beginning, that's interesting. And then a lot of religious people said, oh, a Catholic priest says that, in fact, there was a beginning, because before then, no one knew how to think of a beginning of the universe. It was not a thought. It's not that they thought about it and said there wasn't. It's like, of course, the universe was always here.
Right.
How could everything that there is have a beginning? So we have Einstein's equations. Georges Lemaitre says there's a beginning, and then everyone is jumping on that, saying, see, Genesis is true. God's made the beginning. And so he said, no, this ain't got nothing to do with Genesis. Okay? There was a little spat between the religious folks who were reaching for this scientific result and the Catholic priest who came up with the result, who was in denial of it confirming biblical Genesis. That's all.
Oh wow. Look at and he was Catholic. That's
And he was
that's not
Catholic.
that's kind of rough when your
Yeah.
own people are just like, nah. That's it's kind of like you appoint a special counsel and he goes, "Yeah, there was no fraud in this election." And you go, "Yeah, you're fired."
In that scenario, until you have data to show which version of these, what variant on this equation is operating, you could have a cycling universe. And this is how old I am. When I was in graduate school, we explored all of these solutions to the equation. But we know now from data that we're on a one-way trip. The universe will never recollapse. So no, we're not going to have a collapsing universe. And the birth of the universe, could it have been a universe before that collapsed and then get birthed us again? We don't know.
Oh, okay. Well, there
It
you
would
go,
be
buddy.
hard to have a collapsing system expand and then never recollapse.
Right.
You see what I'm saying? So, because whatever made it collapse should make it collapse again, and there's nothing out there that's going to make that happen. So,
Interesting. There you go. So this is Gaud Haraginadoni, or Haraginadani says this. I'm from San Jose, California. My question regarding shyness of dark matter when interacting with other matter. If we think dark matter as a giant spiderweb that holds the earth and the sun and the gravity, why does it interact with dark matter that holds the earth and the moon together? Or the dark matter that holds our solar system and the Milky Way in the galaxy? With normal matter, these three spiderwebs would scrape and break each other. Dark matter is pretty outgoing all over the place, holding galaxies together and whatnot. But when it comes to interacting with other dark matter, why is it so bashful? Is it because it's afraid of rejection? Or maybe it's just not interested in a three-way, or whatever reason? I'm just curious. Please let me know.
so
Different
dark
parts
matter
of it.
is not holding Earth together.
Right.
The molecular forces are, the electromagnetic attraction forces are. Dark matter is not holding the solar system together. All the objects there is sufficient gravity to make that happen. But dark matter is holding together the galaxy, and it's holding together galaxy clusters. So it turns out, other than through gravity, we don't interact with dark matter. So you could just walk through dark matter, you wouldn't know it, and it wouldn't know it. More accurately said, you wouldn't know it, and it wouldn't care. Okay? So now, not only do you not interact with dark matter does not interact with itself.
Ooh.
Because if it did, you would have concentrations of dark matter. Just think about it. If you have two hot marshmallows and they meet at night, okay, over the fire,
Right.
what'll they do?
They'll stick to each other.
Okay, so
Right.
there are forces within the marshmallow, material forces, that when it sees other marshmallows, that they'll stick. Okay, so our matter knows how to do this. All right, that's how you get planets. That's how
Right.
you get stars.
Right.
Dark matter does not stick to us, so it's not with the marshmallow or with the planet or with the star, and it doesn't stick to itself. So dark matter does not make concentrations. So as far as we know and understand the behavior of dark matter, you don't expect to see dark matter planets or
Right.
dark matter galaxies. The interesting part is that it doesn't even interact with itself physically, only through the force of gravity.
Nice.
So
All right.
watch. You have a forming solar system, and two bits of matter know this, and they fall towards each other and stick. All right?
Right. Right.
Now watch. You have bits of dark matter, all right, and they fall towards each other, and they pass through each
Pass
other.
through each other.
Right, and
Right.
and they'll just rock.
Very
There it is.
rude. Very
Right.
rude.
Very. There you have it.
So this is Bob Dan, and Bobden says this. Hi, this is Bob. Is from the U.S. of A. If space in the universe is expanding, then why aren't we being stretched thin and ripped apart atom by atom? And what am I missing here? I mean, wouldn't the expansion apply at every level? Right down to the subatomic? And how is this current expansion different from the so-called big rip you talk about?
So the expansion of the universe, depending on the rate and where it's happening, it will not overcome the gravitational forces that are and the electromagnetic forces that are otherwise binding solar systems and objects together. The expansion of the universe has to be way stronger
Right.
before that happens. So in other words, yes, you're stretching space, but I'm holding on to myself within the stretching space until the force of the stretching space exceeds that of my gravity or exceeds that of the electromagnetic force. Then it'll pull you apart. So the gravity, if you got a tight gravity system, you're not pulling that apart with your expanding universe yet.
Anyway, this is Michael Rivera. Michael Rivera says, hello, Dr. Tyson and Lord Nice. Michael here from Las Vegas. My question is, would it be possible for humans to artificially create a black hole with significant mass in order to further study the mysteries of how black holes work and what they do? If so, how dangerous would this be, this artificial black hole made here on Earth at a sustainable size? And would there be any way of containing it?
So, yeah, you wouldn't know how to contain a black hole. We don't know how to manipulate a black hole.
Right.
And so maybe someday we could like bunch up space-time and make a little container out of, I don't know. I don't know. So yeah, this would be a really bad idea because a black hole is a voracious eater. So let's say you had a black hole on your desk and it fell to the floor.
Right.
It would start eating Earth. And it would just fall through Earth, eating any part of Earth that was near it. And it would continue to do this until the entire Earth was inside the black hole. And you know how big an Earth mass black hole is?
No.
About the size of a plum.
Oh, wow, that's crazy.
That's a sad day for Earth.
That's a
So-
sad day.
So your black hole eating Earth would become the size of a plum.
Wow.
That's the entire Earth fitting inside the
Entire
black hole.
Earth inside the black hole.
Yeah.
Right. Yeah.
Yeah.
All right. This is Captain James Riley. He says, why do galaxies form a web or a sponge-shaped structure? It seems that on small scales, gravity forms spheres and disks. So I'm a little confused.
Oh, good question. Right, the large-scale structure of the universe is not with galaxies equally spread. It's not with galaxies all in tidy spheres, although some galaxy clusters are. For example, the Coma cluster of galaxies. This is a cluster of galaxies that lines up with the stars in the constellation called Coma, okay? A Coma Berenices, so it's the hair of Bernice, okay? So, yeah, if you look at on constellation maps from like centuries ago when they used to draw this stuff. It's just somebody's hair. Okay, so the Coma cluster, that's a nicely spherical cluster of galaxies. And in fact, that's the first galaxy cluster where dark matter was discovered. Because you looked at all the speeds of the and there's a certain amount of mass, gravity required to keep all of them in this ball. Whole galaxies now, thousands of galaxies. I think like maybe 800. I forgot the exact number, but it's around 1,000 galaxies, and many hundreds. And so you calculate that up, and you find out that it needs like 10 times that much mass to keep the galaxies contained. If you add up the mass of every galaxy, it doesn't add up to the gravity needed to contain them. So that was a guy named Fritz Zwicky in the 1930s, 1936, I think it was, where he's a Caltech, Swiss-born Caltech astrophysicist who discovered this. It's the longest unsolved problem in modern astrophysics, the dark matter problem, birthed with his observations. Anyhow, there are some galaxy clusters that are nice spherically shaped. Others, you see these filaments. It's as though you had a sponge and you cut it, and you looked at the cross-section where there's some concentrations of sponge, but mostly there are these sort of bridges between concentrations. That's what the universe looks like, the inside cross-section of a sponge. Here's the problem.
Mm-hmm.
If you look at how fast the galaxy is moving along one filament, and look at the size of the filament, the universe is not old enough for the galaxy to have crossed that filament. So you don't have structures that represent what the galaxies really want to do if they had enough time.
Right.
So that's what's going on here.
Interesting.
Right? So you have systems that are not gravitationally settled in what they should look. The Coma cluster is. All right, and it's a term we use for this. I forgot it. What is it? It's a relaxed cluster is one where, okay, we got this. Everybody's orbiting just the way they should. And they could cross the size of the cluster in the time the universe has been around. So that's how you know everybody's settled into their routines. Any structures bigger than that, they've not had time to settle. And they may never settle, given how long it takes and given how fast the galaxies are moving through space. So yeah, that's how and why we get that.
Wow. Very cool. Lou Perot says this. My question is it possible to see past by looking see the past by looking into deep space? And if so, which direction do we have to look? And also, is it possible to see the Earth by sending a telescope multiple light years away?
Yeah, so only if you can travel faster than light can you see your own past. So you can't do that. So I know what he's saying, but I wanted to lead up to that. So clearly, he knows that the farther out you look, the farther back in time you see.
Right.
Okay, so there are galaxies that are like 65 million light years away from Earth. Okay, from our galaxy.
Wow.
So right now, if they had a super duper telescope and they look towards Earth, what do they see?
If they're seeing us however many light years ago.
65 million years ago.
Right.
What are they witnessing?
Dinosaurs, right?
Yeah, so the galaxy that's 65 million light years away is witnessing the extinction of the dinosaurs because that light is only now just reaching them.
Right.
Okay. So, but we can't see our own past. That doesn't work. So yeah, but if you send a telescope out there, let's say 1,000 light years away, and then come back, it will be seeing whatever happened here 1,000 years ago.
Right.
Right.
All right. This is Connor Holm. He says, hi, if the Big Rip does occur. A lot of Big Rip questions today. People got it on their mind, man. Connor says, if the Big Rip does occur, what would be the immediate results of tearing of the fabric of space-time? Would these tears be black holes, or would they simply just be voids of nothingness? What is nothing? How could nothing come out of something What would these voids be? Wow.
My simple answer is we have no idea.
Oh,
Okay, the state of the universe post Big Rip is a complete mystery. And what we don't know is there some law of physics that will manifest at that time. Think about that. When do we discover new laws of physics? When we step where we had never previously stepped, when we look where we never previously looked, when we bring a new kind of apparatus, a new kind of detector that we never had before. Then we see the universe behaving in ways we've never seen before. Sends us back to the drawing board to say, is this understandable with previously known physics, or do we have to invent new physics? So
right.
Einstein said to himself, I don't think we'll ever have a black hole, even though his own damn equations predicted it, because a black hole in his equations have infinite density, occupying zero volume in the center of the black hole. And he said, surely there's some new law of physics that's going to show up and save us from ourselves, save us from this mathematical craziness where God divides by zero,
Right.
right? So what happens in the Big Rip? What would it look like? We do not know. And I'd like to know before that day happens so that we can protect ourselves, if that's possible at all. We don't know. And he's wondering if it rips, does nothing show up? Okay? Something we call nothing.
Something we
Does
call nothing.
Okay, but then what is nothing?
What is?
Because is air nothing? Well, you can see through it, but we know there's air there, right? So clearly it's not nothing. So not take away the air. So what's left? Is that nothing? Well, it's still space.
Right.
Well, it's empty space. Nothing. And we know from quantum physics that empty space is a seething soup of what we call virtual particles popping in and out of existence. And and this is what we call the vacuum energy. You just Google that, vacuum
Yes.
energy. There's an energy in the vacuum of space that quantum physics puts there. And we thought, hey, that could be the dark energy in the vacuum of space. So you do the calculation for how much dark energy we measure, then you do the calculation for how much pressure is coming in from these virtual particles popping in and out of existence, and we are off by 100 orders of magnitude. It is the biggest mismatch between an observation and a theory that has ever occurred. This is further evidence that we have no clue what dark energy is. Okay.
Wow.
So there it is. Now, could we imagine a place where there's not even these virtual particles? Okay, but then you can't have quantum physics. So, all right, so now we have a place where there's not only not nothing, there's not even the laws of physics.
Right.
Whoa. So could you exist in that nothing?
Yeah.
Because you only exist because they're like molecules hold you together, and and light and energy and you only exist because the laws of
the
physics
something.
allow you to.
Right.
So the best nothing, if the rip gets you there, if you step through that rip, maybe that nothing does not even contain the fabric of empty space.
Look at that.
Because the laws of physics tell us what the fabric of empty space does. So if you take away not only the empty space, but the laws of physics that would describe it, then that's as good a nothing as I can imagine.
I was watching this thing listening to NPR, and they were doing this thing about energy and all the different forms of energy. And then they, for some reason, played a clip from what I know is one of your and my favorite movies, The Matrix. And they played the clip about how the AI basically, after a singularity, saw us as a form of energy, to be used as little batteries. So my question to you is, do we put out enough energy that if something were an AI would say, you know what, I need to put them to work.
Right, 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 right. Yeah, I'm just trying to think if they put you and me in a battery socket. Uh, I say, no, Chuck, we got to be head to toe, right? All right. So this energy described in the Matrix is drawn from the human body. So you can look at our metabolism. All right. If you're a calorie counter, you'll know that there's something called your basal metabolism. So this is the energy you burn, pay or play. Okay. Just for existing.
Just for existing.
Right. And for some people, it's maybe 1,500 calories a day. For me, it's more like I'm bigger. So for average, I'm a little bigger than average. So I'm like 2,000 calories a day is my basal average. Okay. So now, do you realize that the food calorie is written with a capital C? You might not have noticed that.
Yes.
There's a reason for that. Because a physics calorie is written with a lowercase c. Because a food calorie, one food calorie, equals 1,000 physics calories.
Oh, okay.
So when I say I burn 2,000 calories a day, it's 2,000 food calories. It's 2 million physics calories. And what is a physics calorie? It's the amount of energy required to raise the temperature of 1 cubic centimeter of water 1 degree Celsius.
Interesting.
That is 1 calorie.
That's 1 calorie.
Okay? All right. So, once you have all these calories, it's a rate at which you're burning energy. We have a unit of measure for that. It's called watts. Okay? Watts. And so, when you do the math on this, the average person is operating anywhere between 50 and 100 watts.
Okay.
Okay? So, it's like a light bulb, like an 80-watt light bulb. Okay? There's that 80-watt bulb consumes energy at a rate. So do we. We radiate that. Okay? Or we consume that much energy, our circulation and everything else. So what the machines did, the computers did in the Matrix is line us all up and draw the 80 watts of power from every person at all times.
Okay, that's very inefficient.
So the answer is yes, that's how they did the movie. However, it's extremely inefficient.
Yeah.
You know why? You're burning 2,000 calories a day as long as what is happening?
So long as I'm living and breathing.
No. Yeah, well, yes, but
Well, yeah.
more fundamental than that, well, equally as fundamental as that, how long can you keep burning 2,000 calories a day?
I thought you said that was my base.
Where do you think those calories came from? From the food you're eating. So, in order for all of the Matrix people, the people in the pods, to be feeding 80 watts of power to the Matrix has to feed them.
Ooh, that's 8 billion mouths.
Okay, so what I'm saying is, if the
lot.
Matrix is feeding you
Right.
2,000 calories a day so that it can then pull your 80 watts off of you, why use the middleman?
Right.
Just burn the food calories that you're feeding the people. In fact, every time energy changes from one form to another, it's not 100% efficient. You lose some energy to heat. All the time.
Right.
So you look at the energy in a gallon of gasoline, okay? And that gets burned to drive the car. I forgot the number. 80% of that energy goes into heat. It does not go into moving your car forward.
That's funny.
Okay? So this is a fundamental feature of thermodynamics in the universe. So they were being inefficient. So this is their weak point in their storytelling. And I will give them a hall pass because they did everything else so brilliantly. But that one was just plain stupid. because the machines, the computers just would have used the food that they're feeding them and get their energy off of that and leave the people out of it.
Look at that.
But then they wouldn't have had a movie. Yeah.
Cool.
All right. That's all the time we have, Chuck.
Okay. That was
All
fun.
right. So what was that? This was cosmic.
Cosmological curiosity.
Cosmic queries, cosmological curiosities. I got it.
Yeah.
All right.